Welcome back. Tonight, we settle in with the vast, cold clouds of gas and dust that drift through our galaxy like silent fog, where hydrogen molecules huddle together across distances so immense that light itself takes years to cross them. These stellar nurseries, as astronomers call them, hidden within the dark spaces between the stars we see, where gravity works its patient magic over millions of years, drawing matter inward, building pressure and heat, until something remarkable begins to glow in the depths. Before we begin, take a moment to like the video and subscribe, but only if these stories help you drift off peacefully. Now, dim the lights. Pull the blanket a little closer. And together, let us ease gently into tonight's story. The Orion Nebula has long served as humanity's most accessible window into the processes of star formation, a vast and luminous cloud of gas and dust that hangs in the winter sky like a soft smudge of light, visible even to the unaided eye on clear evenings when one knows where to look. At a distance of approximately 1,344 light-years from Earth, this nebula represents the closest major stellar nursery to our own solar system, close enough that our telescopes can resolve individual structures within its glowing expanses, close enough that we can study the delicate processes by which new stars emerge from the primordial material that drifts between the older stars of our galaxy. To gaze upon the Orion Nebula is to witness star birth in progress, a slow and patient unfolding that has been continuing for millions of years and will continue for millions more, long after our own brief moment of observation has passed into memory. The nebula appears to the naked eye as a faint fuzzy patch in the constellation of Orion, that familiar pattern of stars that graces the northern winter sky and the southern summer sky, depending upon which hemisphere one calls home. More specifically, the nebula occupies what appears to be the middle star in Orion's sword, that short line of stars hanging below the three bright stars of Orion's belt. What seems at first glance to be a single hazy star reveals itself, upon closer inspection or through even modest optical aid, to be something far more extensive, a cloud of glowing material surrounding and illuminated by the young stars embedded within it. Ancient observers noted this fuzzy quality, though they could not have known what they were seeing, could not have understood that this gentle blur of light represented a cosmic nursery where new suns were slowly taking shape from the raw materials scattered throughout interstellar space. The telescopic study of the Orion Nebula began in the early years of the 17th century, when the new technology of the refracting telescope first allowed astronomers to examine celestial objects with greater precision than the unaided eye could provide. In the year 1610, the French astronomer Nicolas Claude Fabry de Peiresc turned his telescope toward the constellation of Orion and recorded his observation of the nebulous region surrounding the stars of Orion's sword. Peiresc was a scholar of wide-ranging interests, a man who corresponded with other learned figures across Europe and who contributed to numerous fields of inquiry, and his observation of the Orion Nebula represents one of the earliest telescopic examinations of this remarkable object. The nebula had certainly been noticed before, its fuzzy appearance distinguishing it from ordinary stars, but Peiresc's observation marked the beginning of a more systematic study that would continue through the centuries that followed. More than a century and a half later, the French astronomer Charles Messier included the Orion Nebula in his famous catalogue of celestial objects, assigning it the designation M42, the 42nd entry in a list that Messier compiled primarily to help comet hunters distinguish between permanent nebulous objects and the transient comets they sought to discover. Messier recorded this entry in 1769, noting the nebula's position and appearance with the careful attention to detail that characterized his work. The Messier catalogue would eventually grow to include over 100 objects, and M42 remains among the most celebrated entries, a designation still used today by amateur and professional astronomers alike when referring to this particular stellar nursery. Messier himself was more interested in comets than in nebulae, yet his systematic cataloguing of these fuzzy patches of light provided a valuable resource for future generations who would come to understand that these objects represented far more than mere obstacles to comet hunting. At the heart of the Orion Nebula lies a tight grouping of young and luminous stars known as the trapezium cluster, so named because its four brightest members form a rough trapezoid shape when viewed through a telescope. These four stars bear the designations Theta-1 Orionis A, B, C, and D, and they represent some of the most massive and energetic stars in the entire nebula complex. The stars of the trapezium are predominantly of spectral types O and B, the hottest and most luminous categories in the stellar classification scheme, and their intense radiation plays a crucial role in shaping the appearance of the surrounding nebula. These young giants pour forth tremendous quantities of ultraviolet light, and this energetic radiation ionizes the hydrogen gas that permeates the nebula, stripping electrons from hydrogen atoms and causing the gas to glow with the characteristic reddish and pinkish hues that make the Orion Nebula such a striking object in astronomical photographs. The most luminous member of the trapezium, Theta 1 Orionis C, proved upon closer examination to be not a single star but a binary system, a pair of stars orbiting their common center of mass in a gravitational embrace that had escaped detection for centuries. This discovery came in 1973, when improved observational techniques revealed the duplicity of this brilliant point of light. The two components of Theta 1 Orionis C orbit each other in a period of approximately 11 years, and the primary star alone possesses a mass roughly 30 to 40 times that of our own Sun, making it a true stellar heavyweight whose eventual fate will likely involve a spectacular supernova explosion millions of years hence. For now, however, this massive binary system continues to flood its surroundings with ionizing radiation, sculpting the nebula gas and contributing to the complex processes of star formation occurring throughout the region. The Orion Nebula that we observe is merely the visible portion of a much larger structure known as the Orion Molecular Cloud Complex, an enormous assemblage of gas and dust that spans approximately 240 light-years across and contains enough material to form many thousands of stars. This vast cloud complex lies behind and around the visible nebula, its denser regions opaque to visible light and therefore hidden from direct observation at optical wavelengths. The visible nebula represents a cavity or blister on the near side of this larger cloud, a region where the radiation from the trapezium stars has ionized and illuminated the surrounding material, creating the glowing spectacle that we observe from Earth. Beyond this illuminated region, extending in all directions, lies the cold and dark molecular cloud, rich in molecular hydrogen and other compounds, quietly harboring the conditions necessary for ongoing star formation. The study of the Orion Nebula underwent a significant transformation with the development of infrared astronomy, which allowed researchers to peer through the obscuring dust that blocks visible light and to observe structures that would otherwise remain hidden. In 1967, astronomers Douglas Kleinman and Frank Lowe conducted infrared observations of the Orion region and discovered a deeply embedded nebula that lay behind the visible portion of M42, a region of intense infrared emission that indicated the presence of very young stellar objects still shrouded in their natal cocoons of dust. This object, now known as the Kleinman-Lowe Nebula, represented a window into an even earlier stage of star formation than could be observed in the visible nebula, a glimpse of stars so young that they had not yet cleared away the material surrounding them. The Kleinman-Lowe Nebula contains some of the youngest known protostars in the Orion region, objects that are still in the process of gathering mass from their surrounding envelopes and that have not yet begun the stable hydrogen fusion that defines a true main sequence star. Perhaps the most significant discovery regarding the Orion Nebula in recent decades came in 1993, when the astronomer C. Robert Adell and his colleagues used the Hubble Space Telescope to obtain high-resolution images of the nebula region and identified numerous small, dark silhouettes against the bright background of ionized gas. These silhouettes proved to be protoplanetary disks, flattened structures of gas and dust surrounding young stars, disks of the same general type from which planets are believed to form. Adell and his team coined the term proplyds, a contraction of protoplanetary disks, to describe these objects, and their discovery provided direct visual evidence that planet formation is a common process accompanying the birth of new stars. The Hubble images revealed over 180 such proplyds within the Orion Nebula, each one a young star surrounded by a disk of material that might eventually coalesce into a system of planets not entirely unlike our own solar system. The proplyds of the Orion Nebula appear in the Hubble images as small, roughly circular, or teardrop-shaped objects, many of them oriented edge-on to our line of sight and therefore appearing as dark bands across the bright nebula background. Some proplyds show bright cusps or edges facing toward the trapezium stars, evidence that the intense radiation from these massive neighbors is gradually eroding the outer portions of the disks, photoevaporating the gas and dust and sculpting the proplyds into their distinctive shapes. This process of erosion means that the protoplanetary disks in the immediate vicinity of the trapezium may have limited lifetimes, their material being stripped away before planets have sufficient time to form. Proplyds located farther from the trapezium, in regions of lower radiation intensity, may have better prospects for planetary formation, though even these disks exist in a challenging environment compared to the relatively isolated conditions in which our own solar system took shape. The presence of so many protoplanetary disks within a single stellar nursery reinforces our understanding that planet formation is not a rare or unusual process, but rather a natural consequence of the way stars form from rotating clouds of gas and dust. When a portion of a molecular cloud begins to collapse under its own gravity, conservation of angular momentum causes the infalling material to flatten into a disk around the central protostar, and this disk provides the raw material from which planets can eventually assemble. The Orion Nebula, with its abundant population of proplyds at various stages of development, serves as a kind of laboratory for studying these processes, a place where we can observe many examples of disk evolution occurring simultaneously, each proplyd representing a slightly different moment in the long journey from primordial cloud to finished planetary system. The light that reaches us from the Orion Nebula tonight departed from that distant stellar nursery some 1,344 years ago, during what was, from an earthly perspective, the late period of antiquity and the early medieval era. The photons entering our telescopes and our eyes were emitted when the nebula appeared much as it does now, the trapezium stars blazing at its heart, the proplyds slowly evolving around their young stellar hosts, the vast molecular cloud complex continuing its patient work of forming new generations of stars. In the time that light has been traveling toward us, the nebula has continued to change, new stars have formed, existing stars have evolved, proplyds have been sculpted and perhaps dispersed, but these changes have been so gradual compared to human timescales that the nebula we observe appears essentially frozen in a single moment of its long history. The processes we study in the Orion Nebula operate on timescales of hundreds of thousands to millions of years, and our observations, spanning only a few centuries since Peiresc first turned his telescope toward this region, represent the merest snapshot of an ongoing cosmic drama. And so the Orion Nebula continues to serve as humanity's primary window into the birthplaces of stars, a nearby example of processes that occur throughout our galaxy and throughout the universe wherever conditions permit the formation of new stellar generations. The nebula hangs in the winter sky as it has for countless millennia, its soft glow marking the location of one of nature's great workshops, a place where the raw materials of interstellar space are slowly being fashioned into new suns and perhaps new worlds. The trapezium stars continue to pour forth their radiation, ionizing the surrounding gas and causing it to fluoresce with colors that our eyes perceive as the gentle pink and violet hues of cosmic nurseries. The proplyds continue their slow evolution, their disks of gas and dust gradually settling and coalescing, perhaps forming planetesimals and protoplanets that may one day become worlds in their own right, orbiting stars that are themselves only now emerging from their long process of formation. There are certain images in the history of science that seem to transcend their original purpose, becoming something more than mere data, something closer to shared human experience, and among all the photographs ever taken of the distant cosmos, perhaps none has achieved quite the same quiet resonance as the image we now call the Pillars of Creation. This photograph was captured on the first day of April in 1995, though it would be released to the public some months later, and it showed something that astronomers had observed before in various forms, yet never quite like this, never with such clarity and strange, almost sculptural beauty. The image was taken by the Hubble Space Telescope, that remarkable instrument orbiting some 300 miles above the Earth's surface, and the principal investigators responsible for this particular observation were Jeff Hester and Paul Scowen, both astronomers working at Arizona State University at the time, who had requested telescope time to study a region of active star formation in a nebula catalogued as Messier 16. The Eagle Nebula, as Messier 16 is more commonly known, lies in the direction of the constellation Serpens, that serpentine pattern of stars visible from much of the Earth during summer months in the northern hemisphere, and though the constellation itself is composed of relatively nearby stars, the nebula behind them is vastly more distant, situated approximately 6,500 to 7,000 light-years from our own solar system. This means, of course, that the light captured by Hubble's instruments on that April day had been traveling through the emptiness of interstellar space for nearly 7 millennia, having left its source around the time when humans on Earth were first developing written language in ancient Mesopotamia. And this long journey of photons across the void is one of those quietly astonishing facts that bears gentle contemplation as you settle into a comfortable position and allow your breathing to slow. The nebula itself had been known to astronomers for some 2.5 centuries before Hubble turned its mirror toward those famous pillars. The original discovery is credited to Jean-Philippe Loys de Chasseaux, a Swiss astronomer who observed and catalogued the object sometime between 1745 and 1746, during those long nights of patient observation that characterized the work of early modern astronomers. De Chasseaux could not have known what he was seeing in any detailed sense, only that there existed in that region of sky a faint smudge of light that was neither star nor planet nor comet, one of those nebulous objects that would puzzle astronomers for another century and more until the true nature of such clouds became clear. The nebula would later be independently rediscovered by Charles Messier and added to his famous catalogue, that list of objects compiled specifically so that common hunters would not confuse these fixed smudges with the moving objects they sought, and thus it received its designation as the 16th entry in that catalogue, a number by which it is still commonly known today among those who observe the night sky with modest telescopes from their gardens and balconies. But what Hester and Scowen revealed in 1995 was something far more detailed than anything de Chasseaux or Messier could have imagined, a close examination of a particular region within the larger nebula where columns of dense gas and dust rose like strange monuments against a backdrop of glowing hydrogen. The name Pillars of Creation was applied to these structures shortly after the image was released, a somewhat poetic designation that nevertheless captures something true about what is happening within them. For these columns are indeed locations where new stars are slowly coming into being, where the raw material of future solar systems is gradually condensing under the patient influence of gravity. The 3 main pillars visible in the original image are of varying heights, with the tallest of them stretching an almost incomprehensible 4 to 5 light-years from base to tip, which is to say that if you could somehow travel at the speed of light itself, the fastest speed permitted by the laws of physics as we understand them, you would require 4 to 5 years of continuous travel simply to traverse the length of that single column of gas and dust. These pillars exist at the edge of a much larger cavity within the Eagle Nebula, a region that has been hollowed out and illuminated by a cluster of young, extremely hot stars known collectively as NGC 6611. Among these stars are examples of the O-type spectral class, which represents the hottest, most massive, and most luminous category of stars that exists, objects that burn through their nuclear fuel with tremendous profligacy and emit vast quantities of ultraviolet radiation as a consequence of their extreme surface temperatures. This ultraviolet light is responsible for much of what we see in the image, for it causes the surrounding hydrogen gas to fluoresce, creating that characteristic reddish-pink glow that suffuses emission nebulae throughout the galaxy, and it is also responsible for the gradual destruction of the pillars themselves through a process that astronomers call photoevaporation. Photoevaporation is a gentle-sounding word for what is actually a rather dramatic physical process, though it occurs so slowly by human standards that it appears as perfect stillness in any single image. The intense radiation from the nearby O-type stars heats the surface layers of the pillars, causing gas particles to gain enough energy to escape the gravitational pull of the cloud and stream away into space, much as water evaporates from a puddle on a warm day, though the physics involved is rather different. Over thousands and millions of years, this process is gradually eroding the pillars, sculpting their shapes into the forms we observe today, and eventually, if nothing else intervenes, the pillars will be entirely dispersed, their material scattered back into the general medium of the interstellar environment. The edges of the pillars in the Hubble image show this process in action, with thin layers of illuminated gas forming bright boundaries around the denser, darker material within, giving the columns that distinctive outlined appearance that makes them so visually striking. And yet, even as the pillars are being destroyed from without, they remain places of creation within. At the tips of the pillars and along their edges, astronomers have identified small, dense regions known as evaporating gaseous globules, often abbreviated to the somewhat whimsical acronym EGGS, and these structures represent sites where new stars are actively forming despite the harsh radiation environment that surrounds them. The eggs are essentially the densest cores of what were once larger cloud structures, regions that have been exposed by the erosion of their outer layers, but which remain dense enough to continue collapsing under their own gravity. Some of these globules contain protostars, objects that have not yet begun hydrogen fusion in their cores but which are well on their way to becoming true stars, and in time, perhaps a few 100,000 years from now, some of these protostars will ignite and begin their lives as main sequence stars, perhaps surrounded by disks of dust and gas from which planets might one day form. The original 1995 image became one of the most widely reproduced astronomical photographs in history, appearing in textbooks, on posters, on the covers of magazines, and in countless documentaries about the cosmos, and its popularity helped to justify the enormous expense and effort that had gone into building, launching, and eventually repairing the Hubble Space Telescope. But science does not stand still, and in the years following that initial observation, new instruments and new observations would add layers of understanding to what the pillars actually are and what their fate might be. In 2007, the Spitzer Space Telescope, which observes the universe in infrared light rather than the visible wavelengths that Hubble primarily uses, turned its attention to the Eagle Nebula and discovered something rather unexpected. The infrared observations revealed what appeared to be a shell of hot dust surrounding the pillars, a structure that some astronomers interpreted as evidence that a supernova explosion, the violent death of a massive star, had occurred somewhere in the vicinity perhaps 8,000 to 9,000 years ago. If this interpretation is correct, and it remains a matter of some scientific discussion, then the shockwave from that ancient stellar explosion may have already reached the pillars of creation and begun the process of destroying them some 6,000 years ago, around the same time that the light we observed in 1995 was beginning its journey toward Earth. This would mean that when we look at the Hubble image, we are not merely looking into the past, as is always the case when we observe distant objects, but we are looking at structures that may no longer exist in their current form, having been disrupted and scattered by an expanding shell of superheated gas and radiation that arrived at their location millennia before their light reached our telescopes. The pillars that we admire in the photograph may be, in a sense, ghostly remnants, images of things that have already passed away, though we will not receive confirmation of this for another 1,000 years or so, when light from the region following the supernova interaction finally reaches us. This uncertainty about the pillar's current state adds a layer of melancholic beauty to the image, though it also illustrates something important about the nature of astronomical observation and the strange relationship between distance, time, and light that governs our understanding of the universe. When we look at the night sky, we are always looking backward in time, seeing things not as they are but as they were when their light began its journey toward us, and for very distant objects, this means we may be observing states of affairs that changed dramatically long before any human civilization existed to wonder about the stars. Hubble returned to the pillars of creation in 2014, nearly 2 decades after the original observation, and this time the telescope captured images in both visible light and near-infrared wavelengths, using upgraded instruments that had been installed during the final servicing mission in 2009. The new visible light image, taken with the Wide-Field Camera 3, showed the pillars in even greater detail than before, with improved resolution and color fidelity that revealed structures too fine to be seen in the original photograph, and the near-infrared image allowed astronomers to peer through some of the obscuring dust that blocks visible light, revealing young stars that were previously hidden within the columns. These newer observations confirmed much of what had been inferred from the original image while adding new details about the distribution of dust, the locations of forming stars, and the ongoing process of photoevaporation that continues to shape the pillar's appearance. The comparison between the 1995 and 2014 images also allowed astronomers to search for changes in the pillars over the intervening 19 years, and while the columns appear essentially identical at first glance, careful measurement revealed subtle differences in the positions of certain features, evidence of the slow but continuous erosion that is gradually reshaping these structures. Jets of material from young stars within the pillars had also changed position slightly, indicating outflow velocities that could be measured by comparing the 2 epochs of observation, and these measurements contributed to a more complete understanding of the star formation processes occurring within the dense clouds. In the end, What makes the pillars of creation such a significant image is not merely its scientific content, though that is considerable, but its ability to communicate something of the vast scale and patient processes of the cosmos to anyone who pauses to look at it. The pillars are at once beautiful and comprehensible, showing structures that resemble clouds or smoke or weathered stone, forms that the human mind can grasp even as the true dimensions and timescales involved exceed any intuitive understanding. They represent a bridge between the alien physics of stellar nurseries and the familiar aesthetic experience of appreciating a striking image, and for many people who have encountered the photograph in books or museums or on screens, the pillars have served as an introduction to the larger wonder of how stars come into being, how matter organizes itself across light years of space, and how the universe continues its slow work of creation and destruction far from any earthly concern. And now, as you rest quietly and allow these thoughts to settle like fine dust in still air, you might let your mind drift among those distant columns, imagining the slow, patient processes that unfold there over timescales that dwarf human history, the gentle accumulation of matter, the gradual ignition of new stars, the eventual dispersal of the clouds back into the emptiness from which they came. Let us turn our attention now to the great cold structures that drift through our galaxy, the enormous clouds of gas and dust that serve as the necessary precursors to all star formation, and these are known to astronomers as giant molecular clouds. They are, in a very real sense, the cradles where stars begin their long existence, though the word cradle perhaps suggests something small and cozy, whereas these objects are anything but small. They stretch across tens or even hundreds of light years, containing enough raw material to form thousands upon thousands of stars, and yet they remain so cold and so quiet that for most of human history we had no idea they were there at all. They are invisible to our eyes, hidden in the darkness between the stars, and only through patient observation with specialized instruments have we come to understand their true nature and their fundamental importance to the ongoing story of our galaxy. A giant molecular cloud is, at its most basic, a region of space where the gas between stars is gathered together in sufficient density and at sufficiently low temperature that the atoms of hydrogen, which make up most of the material, have been able to pair off into molecules. This molecular hydrogen, written by chemists as H2, is a simple thing, just two hydrogen atoms bound together, but its presence marks a profound change in the character of the interstellar medium. In the warmer, more diffuse regions of space, hydrogen exists as individual atoms, sometimes ionized and glowing, sometimes neutral and quiet, but always separate. In the giant molecular clouds, the conditions are different, colder, and denser, and the hydrogen atoms find one another and form these stable pairs, and alongside them gather other molecules in wonderful variety, hundreds of different chemical compounds drifting together in the darkness. The temperatures within these clouds are remarkably low, typically between 10 and 20 Kelvin, which means 10 to 20 degrees above absolute zero on the scale that physicists prefer. To give you a sense of what this means, the freezing point of water sits at 273 Kelvin, so these clouds are more than 250 degrees colder than a winter's day on Earth. They are, in fact, among the coldest places in the known universe, and this extreme cold is not incidental to their role as stellar nurseries but absolutely essential. At higher temperatures, the gas would move too quickly, the thermal energy of the molecules providing enough speed to resist the gentle inward pull of gravity, but at these extraordinarily low temperatures, the molecules drift slowly, almost languidly, and gravity can begin its patient work of drawing them together. The cold, you might say, is what allows stars to be born, and without it the gas would simply remain diffuse and scattered, never condensing into the dense cores that will one day ignite. The density of material within a giant molecular cloud, while high by the standards of interstellar space, would still seem to us like an extraordinarily good vacuum. Typical densities range from 100 to 1,000 molecules per cubic centimeter, and to appreciate how sparse this is, consider that the air you breathe contains roughly 10 to the 19th power molecules in each cubic centimeter, which is to say 10 billion molecules, give or take. A giant molecular cloud is therefore billions of times less dense than the atmosphere around you, emptier by far than the best vacuum chambers we can create in our laboratories on Earth. And yet, compared to the average interstellar medium, where you might find only one atom per cubic centimeter or even less, These clouds represent a substantial concentration of material, enough that gravity can overcome the outward pressure and begin the slow collapse towards star formation. The nearest of these giant molecular clouds to our own solar system lies in the direction of the constellation Taurus, and it is known simply as the Taurus molecular cloud. It sits at a distance of approximately 430 light-years from Earth, which in galactic terms is practically next door, close enough that we can study it in considerable detail with our telescopes and instruments. The Taurus cloud is not the largest or most massive of the giant molecular clouds in our galaxy, but its proximity makes it invaluable for understanding how stars form, and within its cold depths astronomers have observed dozens of young stellar objects in various stages of development. T Tauri stars, those youthful suns still contracting toward the main sequence, take their name from a star in this very cloud, and the study of this region has taught us much of what we know about the earliest stages of stellar life. It stretches across a substantial portion of the sky when viewed with the appropriate instruments, covering an area several times larger than the full moon would appear to our eyes, though of course it is invisible in visible light and must be observed at other wavelengths. This brings us to one of the most interesting challenges that astronomers faced in studying these objects, which is that molecular hydrogen, the primary component of giant molecular clouds, is essentially invisible to us across most of the electromagnetic spectrum. You might think that such an enormous quantity of material would be easy to detect, but molecular hydrogen has a peculiar property that makes it frustratingly difficult to observe. In order for a molecule to emit or absorb light at radio wavelengths, which is how we typically study cold gas, it must possess what physicists call a permanent dipole moment, which is to say an uneven distribution of electrical charge that allows it to interact with electromagnetic radiation. Molecular hydrogen, being composed of two identical atoms, is perfectly symmetrical and has no such dipole moment, and therefore it does not emit radio waves in any easily detectable fashion. It sits there in vast quantities, cold and dark and silent, and we cannot see it directly no matter how carefully we look. The solution to this problem came through the study of other molecules that do produce detectable emissions, molecules that exist alongside the invisible hydrogen and can serve as traces of its presence. The most important of these tracer molecules is carbon monoxide, written as CO, which consists of one carbon atom bound to one oxygen atom. Carbon monoxide does possess a dipole moment, and when its molecules rotate and change their energy states, they emit radio waves at very specific frequencies. The most commonly observed of these emissions occurs at a wavelength of 2.6 millimeters, corresponding to a transition in the rotational state of the molecule, and this emission can be detected by radio telescopes equipped with the appropriate receivers. By mapping the distribution of carbon monoxide across the sky, astronomers could infer the presence and extent of the molecular hydrogen that accompanied it, painting a picture of structures that would otherwise remain entirely hidden from our view. The pioneering work in using carbon monoxide as a tracer of molecular gas was carried out in the 1970s by Philip Solomon and Nicholas Scoville, who conducted extensive surveys of the Milky Way at the 2.6 millimeter wavelength. Their observations revealed for the first time the true extent of molecular material in our galaxy, showing that giant molecular clouds were far more numerous and far more massive than anyone had previously suspected. They found these clouds concentrated along the spiral arms of the Milky Way, gathered in the same regions where young stars and glowing nebulae indicated ongoing star formation, and this correspondence between molecular clouds and stellar birth provided strong evidence that the clouds were indeed the sites where new stars came into being. The work of Solomon and Scoville, built upon by many others in the decades since, transformed our understanding of galactic structure and star formation, and the carbon monoxide line remains one of the most important tools in the study of the cold interstellar medium to this day. One of the remarkable findings that emerged from these surveys was the realization that giant molecular clouds contain a substantial fraction of all the molecular gas in the Milky Way, estimates suggesting that between 30 and 70% of our galaxy's molecular material is locked up within these great structures. This means that if we wish to understand how stars form, we must understand the giant molecular clouds, for they contain the vast majority of the raw material from which new stars can be made. The remainder of the molecular gas exists in smaller clouds and diffuse regions, but the giants dominate the census, and it is within their cold interiors that most of the star formation in our galaxy takes place. This concentration of material is not uniform across the galaxy but follows the spiral structure, with the clouds preferentially found in the arms where the density of matter is highest and the conditions most favorable for their formation. The masses of these clouds span an impressive range, from roughly 10,000 solar masses at the smaller end to as much as 10 million solar masses for the largest known examples. To put this in perspective, a cloud of 1 million solar masses contains enough material to form 1 million stars like our Sun, though in practice the efficiency of star formation is much lower than perfect, and only a small fraction of the cloud's mass will ultimately be converted into stars. The remainder will be dispersed back into the interstellar medium by the energetic processes that accompany star formation, the stellar winds and radiation from newborn stars gradually eroding the cloud from within. A typical giant molecular cloud will persist for perhaps 10 to 30 million years before being disrupted by the stars it has created, a lifetime that seems long by human standards but is brief compared to the ages of the stars themselves. The cloud is a transient structure, constantly forming and dispersing, a temporary gathering of material that enables the birth of objects far more enduring than itself. Within the larger giant molecular clouds, astronomers have identified smaller, denser regions that appear to be in the process of forming individual stars or small groups of stars. Among the most striking of these are the objects known as Bok globules, named after the astronomer Bart Bok who studied them beginning in the 1940s. Bok globules are small, dark, roughly spherical clouds that appear as silhouettes against brighter backgrounds, blocking the light of more distant stars and standing out as inky patches against the glow of emission nebulae. Bart Bok, who was born in the Netherlands and spent much of his career in the United States and Australia, suspected that these dark globules were sites of active star formation, and subsequent observations have confirmed his intuition. Many Bok globules have been found to contain young stellar objects in their earliest stages of development, the dense cores collapsing under their own gravity to form protostars hidden within cocoons of gas and dust. One of the most famous and most studied of these objects is known as Barnard 68, a nearly perfectly spherical dark cloud located at a distance of some 400 light-years from Earth. It appears in photographs as an almost complete absence of background stars, a dark hole punched in the stellar field, and this darkness tells us that the cloud is dense enough to block the light of stars behind it entirely. Barnard 68 has a mass of only a few times that of the Sun, far smaller than the giant molecular clouds we have been discussing, and it spans roughly half a light-year across. Studies of this cloud suggest that it may be in the early stages of gravitational collapse, perhaps only a few 100,000 years away from forming a new star at its center, though such predictions carry considerable uncertainty. It serves as a nearby example of the dense cores within molecular clouds, the small regions where the final stages of star formation are about to begin. The existence of giant molecular clouds and the understanding we have developed of their properties represent one of the great achievements of 20th century astronomy. These vast cold structures, invisible to our eyes and undetectable by our ancestors, contain the seeds of countless future stars, and they continue to form new stars even as we observe them. They are not static objects but dynamic ones, constantly evolving under the influence of gravity, turbulence, magnetic fields, and the feedback from the stars they create. And yet from our distant vantage point, they appear serene, quiet accumulations of gas drifting slowly through the galaxy, and there is something calming in the thought of their patient existence, these cold dark cradles waiting in the spaces between the stars, doing their slow work over millions of years without hurry or urgency, simply being what they are and doing what they do, which is to gather material together until, eventually, in some small region, a new light begins to glow. When we consider the birth of a star, we must begin not with light or heat, but with stillness, with the quiet existence of gas and dust suspended in the vast reaches of interstellar space, waiting, though not consciously of course, for the conditions that might draw it together into something denser and warmer. The question of when such a cloud might begin to collapse under its own gravity was addressed with remarkable clarity by the British physicist and astronomer James Jeans, who in 1902 formulated what we now call the Jeans instability criterion, a mathematical description of the delicate balance between the inward pull of gravity and the outward pressure provided by the thermal motion of gas particles. According to this criterion, a cloud of gas will remain stable, suspended in equilibrium, so long as the internal pressure from the random movements of its molecules is sufficient to counteract the gravitational attraction that every particle exerts upon every other particle. However, when a cloud exceeds a certain critical mass for a given temperature and density, or when it becomes sufficiently cold and dense, the gravitational forces begin to overwhelm the thermal pressure, and the cloud commences its slow, inevitable inward journey. The gene's mass, as it is termed, depends on the temperature of the gas and the density of the material, and for a typical molecular cloud region with temperatures around 10 to 20 Kelvin and densities of perhaps a few 100,000 molecules per cubic centimeter, this critical mass works out to be roughly a few times the mass of our Sun. When a portion of a molecular cloud exceeds this threshold, perhaps nudged toward collapse by the gentle compression from a passing spiral arm or the distant shockwave of an ancient supernova, the material begins to fall inward, slowly at first and then with gathering certainty, though never with anything approaching haste by human standards. The timescale for this initial collapse, known as the freefall timescale, is governed by the density of the material and for typical molecular cloud cores amounts to approximately 100,000 years, a duration that seems immense when measured against a human lifetime yet represents merely a brief moment in the billions of years that a star might eventually shine. During this freefall phase, the collapsing material is essentially transparent to its own radiation, meaning that the heat generated by the compression can escape freely into space, and the cloud remains relatively cool even as it grows denser. This period of isothermal collapse continues until the central regions become dense enough to trap the infrared radiation being produced, at which point the temperature begins to rise more substantially and the collapse slows, forming what astronomers call the first hydrostatic core, a dense concentration of warm gas perhaps a few astronomical units across that represents the earliest identifiable stage in the formation of an individual star. The classification of these young stellar objects into distinct evolutionary stages was systematized by the American astronomer Charles Larder in 1987, who proposed a scheme based on the shape of the infrared spectrum, specifically on how the brightness changes across different infrared wavelengths. This classification system, which has proven remarkably useful for understanding stellar birth, divides protostars into 4 classes, designated somewhat counterintuitively as Class 0, Class 1, Class 2, and Class 3, reflecting a sequence from the most deeply embedded and youngest objects to those approaching the main sequence of hydrogen-burning stars. Class 0 protostars represent the earliest observable stage, when the central object is still deeply buried within its natal envelope of gas and dust, invisible at optical wavelengths and detectable only at far infrared and submillimeter wavelengths where the cold surrounding material emits its thermal radiation. These objects are characterized by spectral energy distributions that rise steeply toward longer wavelengths, indicating that most of the luminosity is being reprocessed by the thick envelope and re-emitted at these cooler temperatures. The Class 0 phase is thought to last only a few tens of thousands of years, a brief but critical period during which much of the final stellar mass is accumulated through rapid accretion from the surrounding envelope. As the envelope is gradually consumed or dispersed, the protostar transitions to the Class 1 stage, where the spectral energy distribution becomes somewhat flatter, still rising toward longer wavelengths but less steeply than before, indicating that the envelope has become thinner and some of the light from the warmer central regions can begin to escape. Class 1 protostars are often visible at near-infrared wavelengths and may display significant variability in their brightness as accretion continues in episodic bursts. This phase typically lasts a few 100,000 years, during which the surrounding envelope continues to diminish while an accretion disk becomes an increasingly prominent feature of the system. The Class 2 stage marks a significant transition, as by this point the envelope has largely dissipated and the young star is surrounded primarily by a circumstellar disk of gas and dust rather than a spherical shroud. The spectral energy distribution of a Class 2 object shows excess infrared emission above what would be expected from the star alone, this excess arising from the warm disk material heated by the central star, but the spectrum no longer rises toward longer wavelengths and instead declines, indicating that the cooler envelope has been cleared away. It is during this Class 2 phase that we encounter the famous T Tauri stars, a category of young variable stars named after their prototype, T Tauri. which was discovered by the English astronomer John Russell Hind in October of 1852 during his systematic survey of variable stars in the constellation Taurus. T Tauri itself proved to be a remarkable object, displaying irregular variations in brightness and a distinctive spectrum showing emission lines that indicated hot gas in energetic motion around the star. We now understand T Tauri stars to be young stellar objects with masses similar to or somewhat less than our Sun, still contracting toward the main sequence and accreting material from their surrounding disks. They exhibit a range of fascinating phenomena, including strong stellar winds, enhanced magnetic activity, and occasional dramatic changes in brightness, all of which reflect the turbulent processes occurring as these stars continue their journey towards stable hydrogen fusion. Finally, Class 3 objects represent the most evolved stage in this classification scheme, where the circumstellar disk has become optically thin or has largely dispersed, and the spectral energy distribution resembles that of a normal stellar photosphere with little or no infrared excess. These objects are sometimes called weak-line T Tauri stars because their spectra show weaker emission features than their more actively accreting Class 2 counterparts, indicating that the accretion process has largely ceased and the star is approaching the stability of the main sequence. One of the most important physical principles governing the collapse process is the conservation of angular momentum, which ensures that any slight rotation present in the original cloud core becomes amplified as the material contracts to smaller radii. Just as a figure skater spins more rapidly when drawing their arms inward, the collapsing gas rotates ever faster as it falls toward the center, and this rotation prevents the material from falling directly onto the forming star. Instead, the gas settles into a flattened disk orbiting the protostar, with material gradually spiraling inward through the disk as friction and magnetic interactions allow angular momentum to be transported outward. These accretion disks, which can extend for hundreds of astronomical units from the central star, are not merely incidental features of the star formation process but play essential roles in regulating the rate at which material reaches the star and in providing the environment where planets may eventually form. The accretion of material through these disks does not proceed at a constant rate, and young stellar objects frequently display variability in their brightness that reflects changes in the accretion flow. Among the most dramatic examples of this variability are the Fu Orionis outbursts, named after the star Fu Orionis in the constellation Orion, which underwent a remarkable brightening event between 1936 and 1937. Over the course of approximately 1 year, Fu Orionis increased in brightness by about 6 magnitudes, corresponding to a factor of roughly 250 in luminosity, transforming from an obscure faint star into a readily visible object. This dramatic increase is understood to result from a sudden enhancement in the accretion rate through the disk, perhaps triggered by gravitational instabilities in the disk material or by the infall of a dense clump of gas, which causes the inner disk to heat up enormously and outshine the star itself. Fu Orionis outbursts appear to be relatively rare, with only a few dozen such events having been identified, but they may represent an important phase through which many or even most young stars pass during their formation. The enhanced accretion rates during these outbursts, which can exceed 100,000th of a solar mass per year compared to typical rates 100 times lower, may allow significant amounts of stellar mass to be accumulated in relatively brief episodes punctuating longer periods of more quiescent accretion. Another distinctive signature of the protostellar phase is the presence of powerful jets and outflows that emerge from the polar regions of the star disk system, carrying material away from the forming star at velocities of hundreds of kilometers per second. When these jets collide with the surrounding molecular cloud material, they create bright shock fronts that can be observed at optical wavelengths, objects that we now call Herbig-Haro objects after the two astronomers who first recognized them as a distinct class of nebulae. George Herbig, working at Lick Observatory in California, and Guillermo Haro, working at the Tonant-Sintler Observatory in Mexico, independently identified and catalogued these peculiar nebular patches in 1951 and 1952, noting their small size, their unusual spectra dominated by emission lines, and their frequent association with young stars. We now understand Herbig-Haro objects to be the visible manifestations of the interaction between protostellar jets and the interstellar medium, shock fronts where the fast-moving jet material decelerates and heats up, exciting the surrounding gas to emit light. These objects often appear in chains or sequences along the jet axis, representing successive ejection events from a central star, and their proper motions across the sky can be measured over periods of years, confirming velocities consistent with the jet interpretation. The jets themselves are thought to be launched from the innermost regions of the accretion disk, where magnetic field lines threading through the disk become wound up by the rotation and channel material along the rotation axis, though the precise mechanisms remain subjects of ongoing research. As the protostar contracts and heats up, it eventually reaches temperatures in its core sufficient to initiate nuclear reactions, though not immediately the hydrogen fusion that will eventually power it through most of its life. The first nuclear burning to occur is the fusion of deuterium, a heavy isotope of hydrogen containing 1 proton and 1 neutron in its nucleus, which can undergo fusion reactions at temperatures around 1 million Kelvin, substantially lower than the 15 million Kelvin required for ordinary hydrogen fusion. Deuterium, though present in only trace amounts, roughly 1 part in 100,000 relative to ordinary hydrogen, provides a modest source of energy during the later stages of protostellar contraction, slowing but not halting the continued collapse. The deuterium burning phase represents an important milestone in the journey towards starhood, distinguishing true protostars from the less massive brown dwarfs, which never achieve the temperatures necessary for sustained hydrogen fusion but may nonetheless burn their deuterium during their youth. For objects destined to become true stars like our Sun, the deuterium burning eventually exhausts the available fuel, and contraction resumes until the core temperatures rise high enough, around 10 to 15 million Kelvin, to ignite the proton-proton chain reaction that fuses ordinary hydrogen into helium. At this point, the star achieves hydrostatic equilibrium, with the energy generated by nuclear fusion balancing the gravitational contraction, and the long main sequence phase of stable hydrogen burning begins, a phase that for a star like our Sun will last approximately 10 billion years. The journey from a diffuse cloud of molecular gas to an ignited star, a journey governed by the physics of gravitational instability first described by James Jeans, shaped by the conservation of angular momentum, and marked by the stages of the Larder classification system, the variability of T Tauri stars, the dramatic outbursts of Fu Orionis events, and the graceful arcs of Herbig-Haro jets. This journey takes only a few million years from start to finish, a mere moment in cosmic terms, yet encompasses transformations of extraordinary magnitude, from cold gas at 10 Kelvin to a blazing core at millions of degrees, from diffuse material spread across light years to a compact sphere releasing energy that will warm planets for billions of years to come. The Carina Nebula rests in the southern sky as one of the most extensive stellar nurseries we can observe within our own galaxy, a vast expanse of glowing hydrogen and embedded stars that stretches across more than 300 light-years of space, which is to say it spans a distance that light itself, traveling at its constant and unhurried pace of nearly 300,000 kilometers each second, would require more than 3 centuries to cross from one edge to the other. This nebula, catalogued formally as NGC 3372, lies approximately 7,500 light-years from our own solar system, positioned along one of the spiral arms of the Milky Way where the conditions for star formation have been particularly favorable for millions of years, and where new generations of stars continue to emerge from the dense clouds of gas and dust that fill this region with their characteristic reddish glow. The nebula belongs to a class of objects astronomers refer to as HO regions, which is a designation indicating that the hydrogen gas within has been ionized, meaning that the electrons have been stripped away from the hydrogen atoms by the intense ultraviolet radiation pouring forth from the hot young stars embedded throughout the cloud. This ionization process is what gives the nebula its distinctive appearance, for when those freed electrons eventually recombine with hydrogen nuclei, they release energy in the form of light, and much of that light falls within the red portion of the visible spectrum, which explains why HI regions tend to display those soft reddish and pinkish hues that make them so recognizable in astronomical photographs. The Carina Nebula represents one of the largest such regions in the entire Milky Way galaxy, exceeded in apparent size only by the Tarantula Nebula in the Large Magellanic Cloud, though that object lies in a neighboring galaxy rather than within our own. European astronomers first recorded the Carina Nebula during an era when systematic observation of the southern skies was still in its early stages, for much of the southern celestial hemisphere remained poorly mapped compared to the northern regions that had been studied since antiquity from observatories in Europe and the Middle East. The French astronomer Nicolas Louis de Loci undertook an ambitious program to catalogue the southern stars during an expedition to the Cape of Good Hope in 1751 and 1752, where he set up his instruments and spent months carefully recording the positions and brightnesses of thousands of celestial objects that were invisible from European latitudes. It was during this patient work at the southern tip of Africa that Loci noted the existence of the nebulous region we now call the Carina Nebula, adding it to his growing catalogue of southern sky objects and thereby bringing it to the attention of the broader astronomical community, though the true nature and extent of this stellar nursery would not be appreciated until later centuries brought more powerful telescopes to bear upon it. Within this great nebula lies a star that has captured the attention of astronomers for nearly 2 centuries, a massive and unstable object known as Eta Carinii, which underwent one of the most remarkable stellar outbursts ever recorded in the middle of the 19th century. The great eruption of Eta Carinii began around 1837 and continued through 1856, a period during which this distant star brightened so dramatically that it briefly became the second brightest star visible in the entire night sky, outshone only by Sirius, which lies a mere 8.5 light-years from Earth compared to Eta Carinii's distance of more than 7,000 light-years. For a star at such an enormous distance to appear so brilliant to observers on Earth, it must have been releasing energy at a truly extraordinary rate, and indeed astronomers now estimate that during the peak of this eruption, Eta Carinii was radiating energy at millions of times the luminosity of our own Sun. The cause of this great brightening was not a supernova explosion, as one might expect from such a dramatic increase in luminosity, but rather a massive ejection of material from the star's outer layers, a process that expelled somewhere between 10 and 40 solar masses of gas and dust into the surrounding space over the course of those 2 decades. This ejected material did not disperse uniformly in all directions but instead formed a distinctive bipolar structure, 2 rounded lobes extending outward from the central star like the 2 halves of an hourglass or, as some have suggested, like a small figure or homunculus, which is the name that has been given to this structure, the homunculus nebula. The homunculus continues to expand outward at velocities of several hundred kilometers per second, carrying with it the material that Eta Carinii shed during its 19th century paroxysm, and astronomers can still observe this structure today, measuring its gradual expansion and using those measurements to trace backward to the timing of the original eruption. The astronomer John Herschel, son of the famous William Herschel who discovered Uranus, observed the Carina Nebula during his own expedition to the Cape of Good Hope in the 1830s, and it was Herschel who gave a name to one of the nebula's most distinctive features, a dark silhouette visible against the brighter background of glowing gas. This feature he called the Keyhole Nebula, for its shape reminded him of an old-fashioned keyhole, that elongated aperture through which one might peer to see what lies beyond a locked door. The keyhole is what astronomers term a dark nebula, meaning that it is a dense concentration of gas and dust that does not glow with its own light but instead blocks the light from the brighter nebulosity behind it, casting a shadow of sorts against the luminous backdrop. Such dark nebulae represent regions where the material has not yet been reached by the ionizing radiation of nearby stars, or where the density is so great that light cannot penetrate, and they often serve as sites where new stars are forming, hidden from our view within their dusty cocoons. The Carina Nebula contains not only individual remarkable stars but also entire clusters of young and massive stars, associations that form together from the same parent cloud and remain gravitationally bound to one another as they orbit through the nebula. Among the most notable of these are the clusters designated Trumpler 14 and Trumpler 16, named after the Swiss-American astronomer Robert Julius Trumpler, who catalogued numerous open star clusters during the early 20th century. Trumpler 16 is the home of Eta Carinii itself, along with numerous other hot and luminous stars that collectively contribute to the ionization of the surrounding nebula, while Trumpler 14 lies nearby and represents one of the youngest known open clusters in the Milky Way, with an estimated age of less than 1 million years, which is remarkably brief on the timescales of stellar evolution. The stars within Trumpler 14 are still surrounded by remnants of the gas and dust from which they formed, and many of them belong to the hottest and most massive spectral classes, burning through their nuclear fuel at rates that will limit their lifetimes to mere millions of years rather than the billions of years that smaller and cooler stars like our Sun can expect. Among the luminous stars inhabiting this region is one that stands out even in such distinguished company, a star designated WR25, which belongs to the category known as Wolf-Rayet stars. These are massive stars that have evolved beyond the main sequence phase of their lives and have begun shedding their outer layers through powerful stellar winds, exposing the products of nuclear fusion that were once hidden deep within their cores. WR25 is estimated to possess a luminosity exceeding 6 million times that of our Sun, making it one of the most intrinsically luminous stars known anywhere in the galaxy, a beacon of such intensity that if it were placed at the distance of Sirius, it would appear bright enough to cast shadows on Earth and would be clearly visible during the daytime. The energy output of such a star is almost impossible to grasp in everyday terms, for it represents a rate of energy release that dwarfs anything we experience on human scales, yet the star itself, despite its extraordinary luminosity, remains invisible to the unaided eye due to its great distance from us, another reminder of the vast scales over which the universe operates. In April of 2010, to commemorate the 20th anniversary of the launch of the Hubble Space Telescope, astronomers released an image of a dramatic pillar of gas and dust within the Carina Nebula, a structure they informally named Mystic Mountain. This pillar rises approximately 3 light-years in height from its base, a column of dense material that has been sculpted by the radiation and stellar winds from the nearby hot stars, much as the famous pillars in the Eagle Nebula were shaped by similar processes. The top of the pillar shows evidence of jets emerging from newly forming stars hidden within the dusty column, young stellar objects that are still in the process of gathering material from their surroundings and channeling some of that material into narrow outflows that extend perpendicular to the accretion disks from which they feed. The name Mystic Mountain was chosen to evoke the ethereal and otherworldly appearance of the structure, though the physics governing its formation and evolution are quite well understood, involving the interplay between radiation pressure, gravitational collapse, and the hydrodynamics of the surrounding medium. The processes unfolding within the Carina Nebula represent star formation on a grand scale, the sort of vigorous and prolific stellar birth that occurs only in the largest and most massive of molecular clouds, where the available raw material is sufficient to produce not just a few stars but entire associations containing thousands of new objects spanning the full range of stellar masses. The most massive of these newborn stars will live fast and die young, exhausting their nuclear fuel within a few million years and ending their lives in supernova explosions that will further enrich the surrounding medium with heavy elements, seeding future generations of star formation with the materials necessary to build rocky planets and, perhaps, to support the eventual emergence of life. The less massive stars will live longer, gradually dispersing from their birth clusters and spreading throughout the galaxy, carrying with them the chemical signatures of their origin in this particular region of space. For now, the Carina Nebula continues its patient work of stellar creation, converting interstellar gas into new stars at a rate that has remained roughly constant for millions of years, a process that will likely continue for millions more until the available material is exhausted or dispersed by the cumulative effects of stellar winds and supernova explosions. The light from this distant nursery takes more than 7 millennia to reach our eyes, meaning that what we observe today actually occurred during an era when human civilization on Earth was just beginning to develop writing and build its first cities, and the current state of the nebula will not be known to future generations for another 7,500 years, by which time the processes of star formation may have advanced or declined in ways we cannot predict. This is the nature of astronomical observation, this gentle delay between event and perception, this acceptance that we see the universe not as it is but as it was, and that our understanding must always account for the finite speed with which light carries information across the cosmic distances that separate us from the objects of our study. When we look up at the night sky on a clear evening, we might notice that the stars appear to vary somewhat in brightness, with a few brilliant points of light scattered among countless fainter ones, and this simple observation, made by countless generations of stargazers before us, actually hints at something rather profound about the way the universe makes its stars, for it turns out that stellar nurseries do not produce all stars equally, but instead follow a remarkably consistent pattern that favors the creation of small, dim stars over large, luminous ones, a pattern so reliable that astronomers have given it a name and spent decades working to understand just why it should be so. The story of our modern understanding of this pattern begins in the middle of the 20th century, in a time when astronomers were beginning to piece together the processes by which stars form from collapsing clouds of gas, and it was in this era that a young physicist named Edwin Salpeter, working at Cornell University in the United States, published a paper that would prove to be one of the most influential contributions to stellar astrophysics of its century, a paper that appeared in the Astrophysical Journal in 1955 and bore the rather technical title of The Luminosity Function and Stellar Evolution, though its contents would come to be known by a simpler name, the initial mass function. What Salpeter had done, through careful analysis of the stars in our local neighborhood of the galaxy, was to work out how many stars of each mass were being produced whenever a batch of new stars formed from a collapsing cloud, and his findings revealed something both elegant and surprising, for the distribution of stellar masses followed what mathematicians call a power law, which is to say that the number of stars at any given mass could be predicted by a simple mathematical relationship, involving that mass raised to a particular exponent, and this relationship showed that for every increase in mass, there were progressively fewer stars, so that massive stars were genuinely rare while low-mass stars were extraordinarily common, like a cosmic preference for modesty over grandeur. The specific form of this relationship, which astronomers still refer to as the Salpeter initial mass function in honor of its discoverer, indicated that if you were to survey all the stars being born in a particular stellar nursery, you would find that the overwhelming majority of them were small, cool, and rather faint, belonging to the class we now call red dwarfs, while only a tiny fraction would grow to become the brilliant blue giants that dominate our photographs of nebulae, and this finding has been confirmed again and again across decades of observation, in star-forming regions throughout our own galaxy and in galaxies far beyond, suggesting that whatever process determines stellar masses operates in much the same way throughout the observable universe. To put some numbers to this pattern, we can say that roughly 3/4 of all stars, perhaps 75% or thereabouts, belong to the red dwarf category, with masses less than half that of our own Sun, and these modest little stars, while individually inconspicuous, collectively account for the vast majority of stellar objects in any galaxy, burning their hydrogen fuel so slowly and efficiently that they will continue to shine for tens or even hundreds of billions of years, far longer than the current age of the universe. And so in a sense the cosmos is primarily populated by these patient, long-lived embers rather than by the spectacular but short-lived giants that capture so much of our attention. Understanding why stars should form with this particular distribution of masses has been one of the great projects of theoretical astrophysics in the decades since Salpeter's original paper, and the answer, as it turns out, lies in the complex physics of how molecular clouds fragment as they collapse under their own gravity, for a cloud does not simply shrink down uniformly to form a single star, but instead breaks apart into many smaller pieces, each of which may then collapse further to form an individual star or perhaps a close binary pair, and the way this fragmentation proceeds depends on a delicate balance between gravity, which pulls matter inward, and various forms of pressure, including thermal pressure from the warmth of the gas and turbulent pressure from the chaotic motions within the cloud. As a region of a molecular cloud begins to collapse, it develops denser patches here and there, irregularities that arise naturally from the turbulent flows within the gas, and these denser patches have stronger gravitational pull than their surroundings, which allows them to attract still more material and grow denser yet, and if such a patch becomes dense enough, it may reach a critical threshold where its self-gravity overwhelms the supporting pressure and it begins to collapse independently of the larger cloud, becoming what astronomers call a prestellar core, a small pocket of gas destined to form one star or perhaps a small group of stars, and the mass of this core will largely determine the mass of the star or stars it eventually produces. The physics of this fragmentation process naturally favors the creation of many small cores rather than a few large ones, because smaller regions require less mass to become gravitationally unstable and begin collapsing on their own, and this tendency is reflected in the shape of the initial mass function, which shows that low-mass stars greatly outnumber their more massive siblings, though the precise details of how core masses translate into stellar masses involve additional complications that researchers have spent decades working to understand, including the effects of magnetic fields, radiation from nearby stars, and the accretion of additional material onto forming protostars. In the years following Salpeter's pioneering work, astronomers continued to refine our understanding of the initial mass function, using ever more powerful telescopes to survey star-forming regions and count stars of different masses. And one particularly important contribution came from Pavel Krupa, an astronomer working in Germany, who published a comprehensive analysis in 2001 that revealed additional structure in the mass distribution at low stellar masses, structure that Salpeter's original power law had not captured, for while Salpeter's relationship worked well for stars more massive than our Sun, Krupa's work showed that the distribution turned over below about half a solar mass, meaning that the number of stars did not continue to increase as steeply at the lowest masses, but instead flattened out and eventually began to decline as one approached the minimum mass necessary for a star to sustain hydrogen fusion in its core. This minimum mass, below which an object cannot generate sufficient pressure and temperature at its center to ignite the nuclear reactions that define true stars, sits at approximately 8% of the Sun's mass, or about 80 times the mass of Jupiter, and objects that form through the same collapse processes as stars but end up below this threshold are known as brown dwarfs, sometimes called failed stars, though this term perhaps does them a disservice, for they are fascinating objects. In their own right, glowing dimly from the heat of their gravitational contraction and gradually cooling over billions of years, never achieving the self-sustaining fusion that would allow them to shine as true stars, and Krupa's refinements to the initial mass function helped to clarify the boundary between these brown dwarfs and the smallest true stars, the red dwarfs that form the bulk of the stellar population. The question of what determines the final mass of a star has inspired several competing theoretical frameworks over the years, and among the most influential has been the theory of competitive accretion, developed primarily by Ian Bonnell and his collaborators during the 1990s and early 2000s, which proposes that the stars forming within a cluster are not isolated from one another but instead compete for the available gas, with those protostars that happen to find themselves near the center of the cluster, where the gas density is highest and the gravitational potential deepest, having access to more material and therefore growing to larger final masses, while those on the outskirts must make do with less and end up as smaller stars. So that the mass of a star is determined not just by the initial conditions of the core from which it formed, but also by its location within the forming cluster and its success in this competition for raw material. An alternative view, known as turbulent fragmentation, holds that the mass distribution of stars is largely set by the fragmentation process itself, with the turbulent motions within molecular clouds creating a spectrum of core masses that directly maps onto the final stellar masses, so that the initial mass function is essentially a reflection of the way supersonic turbulence structures the gas before collapse even begins. And while both theories capture aspects of the truth, current thinking suggests that the real situation involves elements of both, with turbulent fragmentation setting the initial conditions and competitive accretion modifying the outcome as the cluster evolves, and numerical simulations that incorporate both processes have had considerable success in reproducing the observed initial mass function, lending support to this synthetic view. At the opposite end of the mass spectrum from the brown dwarfs and red dwarfs, we find the rare and spectacular massive stars, those stellar giants that contain tens or even hundreds of times the mass of our Sun and burn through their nuclear fuel in just a few million years. And for many decades astronomers believed that there was an upper limit to how massive a star could become, a ceiling imposed by the physics of radiation pressure. For as a star grows more massive it becomes more luminous, and at some point the outward pressure of its radiation becomes strong enough to blow away any additional material that tries to fall onto the star, halting its growth, and theoretical calculations suggested that this limit lay somewhere around 150 solar masses, beyond which stars simply could not exist. This theoretical limit stood largely unchallenged until the early 21st century, when observations of a remarkable cluster of stars in the Large Magellanic Cloud, one of the satellite galaxies orbiting our own Milky Way, began to suggest that nature had found ways around this supposed barrier, for within the Tarantula Nebula, also known as 30 Doradus, lies a dense stellar cluster called a 136, and at the heart of this cluster reside some of the most massive stars ever discovered, including one designated a 136A1, which was found in 2010 to have a mass of somewhere between 250 and 315 solar masses, depending on the analysis, far exceeding the old theoretical limit and forcing astronomers to reconsider their understanding of how massive stars can grow. The work of Philip Massey and his collaborators, along with that of Danny Lennon, Paco Nahoro, and others, has been instrumental in characterizing these extraordinary objects, using spectroscopy to determine their temperatures, luminosities, and masses, and their findings have shown that while stars as massive as a 136A1 are exceptionally rare, forming perhaps only a handful in an entire galaxy at any given time, they do indeed exist, and their presence tells us that under the right conditions, the accretion processes that build stars can continue to feed material onto a growing protostar even against the fierce radiation pressure that would seem to prevent it, perhaps through disk accretion or through mergers of smaller stars in dense cluster environments. The existence of these stellar behemoths does not overturn the initial mass function, which still shows that such massive stars are extraordinarily rare, but it does extend our understanding of what the universe is capable of creating in its most prolific stellar nurseries, and researchers continue to debate exactly where the upper mass limit truly lies, or indeed whether there is a sharp cutoff at all rather than a gradual decline in the probability of forming ever more massive stars, and observations of other dense clusters, both in our galaxy and beyond, may eventually provide the data needed to settle this question, though for now the Tarantula Nebula remains the best laboratory for studying the most extreme examples of stellar mass. And so we come to appreciate that the initial mass function, first glimpsed by Salpeter in 1955 and refined by generations of astronomers since, represents one of the fundamental regularities of the universe, a pattern that emerges from the complex physics of collapsing gas and fragmentation and competition and accretion, yet somehow produces the same basic distribution of stellar masses wherever we look, from the nearby Orion Nebula to distant galaxies at the edge of the observable universe. And this pattern tells us that the cosmos, for all its variety and grandeur, has a preference for modest stars, for the small and patient red dwarfs that will still be shining long after the massive blue giants have exploded and faded. And perhaps there is something reassuring in that thought, that the universe builds most of its stars to last. For a very long time, the places where stars are born remained almost entirely hidden from us, not because they were far away, though of course they are tremendously far away, but because they are wrapped in thick blankets of the very dust from which new stars form. Visible light, the kind of light our eyes evolved to see, cannot pass through these dense clouds of microscopic particles, and so for centuries astronomers could only observe the outsides of these stellar nurseries, the glowing edges and the silhouettes against brighter backgrounds, while the actual processes of star formation remained frustratingly obscured. It was rather like trying to understand what happens inside a cocoon by looking only at its surface, or attempting to study the interior of a fog bank while standing outside it on a clear day. The universe, it seemed, had drawn curtains around its most creative work, and we could do little more than guess at what was happening behind them. But light, as you may know, comes in many forms that our eyes cannot detect, and some of these forms have the remarkable ability to pass through dust as easily as visible light passes through clear glass. The story of how we learn to see through cosmic dust is a quiet one, filled with patient instrument building and careful observations, and it begins in earnest with the development of detectors sensitive to infrared radiation, which is a form of light with wavelengths longer than red, the kind of radiation you feel as warmth from a fire or from sunlight on your skin. Infrared light had been known since William Herschel discovered it in 1800 by measuring the temperature beyond the red end of a spectrum, but detecting very faint infrared radiation from distant astronomical objects proved extraordinarily difficult because everything at room temperature, including the telescope itself and the detector and the walls of the observatory, glows brightly in infrared. It would be rather like trying to see a candle while standing inside a furnace. The breakthrough came in 1961, when an American physicist named Frank Lowe developed an ingenious device called the germanium bolometer. A bolometer is a kind of thermometer so sensitive that it can detect the tiny amount of heating caused by individual photons of light striking it, and by using the element germanium cooled to temperatures just a few degrees above absolute zero, Frank Lowe created a detector that could sense far-infrared radiation with unprecedented sensitivity. His bolometer was cooled with liquid helium to approximately 2 degrees above absolute zero, which is minus 271 degrees Celsius, so cold that the detector itself emitted almost no infrared radiation that might interfere with the faint signals from space. This quiet innovation opened a new window onto the universe, and particularly onto those dusty regions where stars are being born, because the dust grains that block visible light so effectively absorb that light and re-emit the energy as infrared radiation. The very substance that hides young stars from our eyes actually glows in infrared, revealing the presence and temperature of material that would otherwise be invisible. The physics behind infrared light's ability to penetrate dust is rather elegant in its simplicity. Dust grains in space are typically quite small, ranging from a few nanometers to perhaps a micrometer in size, and they are most effective at blocking light with wavelengths similar to their own dimensions. Visible light has wavelengths between about 0.4 and 0.7 micrometers, which happens to overlap considerably with the sizes of interstellar dust grains, and so visible light is absorbed and scattered very efficiently. Infrared light, with its longer wavelengths, interacts less strongly with these particles, in much the same way that ocean waves pass around small rocks without being much disturbed while being blocked by larger obstacles. At a wavelength of 2.2 micrometers, which astronomers call the K-band, the extinction caused by dust is only about 10% of what it would be for visible light, and at longer wavelengths the dust becomes even more transparent. This means that by observing in infrared, we can peer into regions that would require visible light to be 10 times brighter to be detectable, or equivalently, we can see through dust clouds that would be entirely opaque to our eyes. In January of 1983, a small satellite called IRAS, the Infrared Astronomical Satellite, was launched into orbit around Earth, and over the following 10 months it surveyed nearly the entire sky at infrared wavelengths ranging from 12 to 100 micrometers. The satellite carried a telescope only 60 centimeters in diameter, but because it was above the Earth's atmosphere and could be cooled to extremely low temperatures, it was far more sensitive than any ground-based infrared observatory that had existed before. IRAS discovered approximately 350,000 infrared sources during its brief mission, including a great many that had never been seen at visible wavelengths, and among these discoveries were hundreds of deeply embedded protostars, young stellar objects still surrounded by and accreting material from their natal clouds. These were stars in the very act of being born, their visible light completely absorbed by surrounding dust, but their infrared glow revealing them clearly. The satellite also discovered the unexpected presence of warm dust around many mature stars, including our own star Vega, which provided the first evidence for debris disks that might indicate the presence of planetary systems, but that is perhaps a story for another time. 2 decades after IRAS, a more sophisticated infrared observatory called the Spitzer Space Telescope was launched in August of 2003. Named after the American astronomer Lyman Spitzer, who had first proposed the idea of space-based telescopes in 1946, this observatory carried a telescope 85 centimeters in diameter and could observe at wavelengths from 3.6 to 160 micrometers with far greater sensitivity and resolution than IRAS had achieved. The telescope was cooled by liquid helium to just 5.5 degrees above absolute zero, and it operated in an unusual orbit trailing behind Earth in its path around the Sun, which kept it far from Earth's infrared glow. One of Spitzer's major accomplishments was a project called GLIMPSE, the Galactic Legacy Infrared Mid-Plane Survey Extraordinaire, which mapped a broad strip along the plane of our Milky Way galaxy, the region where most star formation occurs. Over the course of this survey, Spitzer catalogued more than 400 million individual stars, the majority of which had never been seen before at visible wavelengths because they lie behind or within the dusty lanes that run along our galaxy's disk. The telescope operated until January of 2020, when it was finally retired after more than 16 years of observations, having revealed star-forming regions throughout the galaxy in extraordinary detail. Among the regions studied by Spitzer was a vast and remarkably active stellar nursery called the W51 complex, located approximately 17,000 light-years from Earth in the direction of the constellation Aquila. W51 is one of the most luminous star-forming regions in our entire galaxy, containing enough material to form more than 1 million stars like our Sun, and it hosts some of the most massive and luminous young stars known. At visible wavelengths, W51 is almost invisible, hidden behind and within enormous quantities of gas and dust, but in infrared light it blazes with the glow of countless young stellar objects in various stages of formation. Observations revealed clusters of massive protostars, outflows of gas being ejected at high speeds, and intricate structures in the surrounding molecular material. The complex is so large and so actively forming stars that it has become a kind of natural laboratory for understanding how the most massive stars in our galaxy come into being, and it continues to be studied by new observatories seeking to understand the processes at work within it. But infrared is not the only form of light that can penetrate cosmic dust, and the story of radio astronomy begins with a discovery that was entirely accidental and initially rather puzzling. In 1932, a young engineer named Karl Jansky was working at Bell Telephone Laboratories in New Jersey, investigating sources of static that might interfere with transatlantic radio communications. He built a large rotating antenna, about 30 meters in length, that could detect radio waves at a wavelength of approximately 14.6 meters, and he patiently catalogued the various sources of noise it picked up. He identified static from local thunderstorms and from distant thunderstorms, but there was also a persistent faint hiss that seemed to peak once every 23 hours and 56 minutes, which is the length of a sidereal day, the time it takes for Earth to rotate once relative to the distant stars rather than relative to the Sun. Jansky eventually determined that this radio hiss was coming from the Milky Way itself, strongest in the direction of the constellation Sagittarius, where the center of our galaxy lies. He had discovered, quite by accident, that the universe emits radio waves, and that these waves could be detected from Earth's surface. Radio waves have wavelengths far longer than infrared radiation, ranging from millimeters to meters, and they pass through interstellar dust almost completely unimpeded. This makes radio astronomy extraordinarily valuable for studying the interior of molecular clouds, because the dust that blocks visible light and even partially attenuates infrared has essentially no effect on radio observations. Moreover, many molecules emit or absorb radiation at very specific radio wavelengths, allowing astronomers to detect and identify the chemical composition of distant clouds, and the radio emission from these molecules often traces the coldest, densest regions where star formation is most imminent. The most powerful radio telescope for studying star formation is currently ALMA, the Atacama Large Millimeter and Submillimeter Array, which began full scientific operations in March of 2013. Located on a high plateau in the Chilean Andes at an altitude of 5,000 meters, where the air is thin and dry and absorbs very little of the millimeter wavelength radiation ALMA detects, the observatory consists of 66 individual radio antennas that can be moved into various configurations across the desert. The antennas work together as an interferometer, combining their signals to synthesize the resolving power of a much larger single telescope, and when spread to their maximum separation of 16 kilometers, they can achieve an angular resolution of 0.005 arcseconds, which is sharp enough to see a 10-cent coin at a distance of more than 500 kilometers. This extraordinary resolution allows ALMA to study the detailed structure of protoplanetary disks, the rotating reservoirs of gas and dust around young stars from which planets form, and to observe the intricate motions of gas within collapsing cloud cores. Most recently, the James Webb Space Telescope, launched in December of 2021 and operational since mid-2022, has provided infrared observations of star-forming regions with unprecedented sensitivity and resolution from its position at the second Lagrange point, approximately 1.5 million kilometers from Earth. Among its early observations were stunning images of a region known informally as the Cosmic Cliffs, a portion of the Carina Nebula where intense radiation from nearby massive stars is sculpting towering walls of gas and dust at the boundary of a giant molecular cloud. At visible wavelengths, as seen in earlier images from the Hubble Space Telescope, these cliffs appear as dark silhouettes against the glowing nebula behind them, but in Webb's infrared observations the dust becomes partially transparent, revealing hundreds of young stellar objects previously hidden within the dense material. Many of these are protostars still embedded in their natal cocoons, surrounded by disks of material and launching jets that carve channels through the surrounding gas, and some appear to be binary or multiple star systems in the process of formation. The observations revealed not only young stars but also structures within the dust that hint at the complex dynamics of star formation. where radiation pressure and stellar winds from already formed stars trigger and shape the formation of the next generation. And so, through patient development of new instruments and detectors, through bolometers cooled to temperatures colder than any natural place in the universe, through satellites orbiting high above Earth's obscuring atmosphere, and through arrays of radio antennas spread across high desert plains, we have learned to see what was once invisible. The dust that seemed to hide the births of stars has become instead a kind of glowing screen, radiating in infrared the very energy it absorbs, while radio waves pass through as though the dust were not there at all. What we have found, looking through and beyond that dust, is a universe far richer in forming stars than we ever imagined from visible light alone, where hundreds of millions of young stellar objects glow warmly in their cocoons, slowly gathering the material that will one day ignite in their cores. It is a view that required decades of careful work to achieve, and it continues to grow clearer with each new instrument we send into the sky or plant upon a mountain, showing us the universe as it truly is rather than merely as our limited eyes might perceive it. And so we turn now, gently and without hurry, to the question of what sets these nurseries into motion in the first place. What quiet or sometimes not so quiet events in the cosmos might nudge a cloud of gas from its peaceful drifting state into the slow collapse that will eventually bring new stars into being? For it seems that many stars, perhaps even our own sun and all the worlds that circle it, owe their existence not merely to gravity and time but to specific triggers, to distant events that sent ripples through the interstellar medium and compressed the gas just enough to begin the process of star formation. This is a subject that invites us to consider our own origins, to trace back through billions of years to a moment when something happened nearby, something ancient and powerful, that may have been the very reason our solar system exists at all. The theory that our sun's formation was triggered by a nearby supernova is one that has occupied astronomers for several decades now, and the evidence for it comes to us from the most unexpected of places, from rocks that fell from the sky. In the early morning hours of the 8th of February in the year 1969, a brilliant fireball streaked across the skies of northern Mexico, fragmenting as it descended and scattering thousands of stones across the countryside near the village of Pueblito de Allende in the state of Chihuahua. The meteorite that fell that morning, which came to be known simply as the Allende meteorite, proved to be one of the most significant finds in the history of planetary science, a fragment of the early solar system preserved almost unchanged for 4.5 billion years. Within its dark, carbon-rich matrix, scientists discovered something remarkable: the decay products of radioactive isotopes that should not have been present unless something very energetic had occurred just before the solar system formed. The isotopes in question are aluminum-26 and iron-60, both of which are unstable and decay relatively quickly by cosmic standards. Aluminum-26 has a half-life of only about 717,000 years, which means that half of any given sample will have decayed within that time. Iron-60 has a half-life of approximately 2.6 million years. Both of these timescales are extremely short compared to the age of the solar system, which tells us something important, namely that these isotopes could not have been produced in some ancient stellar event billions of years before our sun formed, for they would have long since decayed into their stable daughter products. Instead, their presence in the Allende meteorite and in other primitive solar system materials indicates that they were freshly synthesized and injected into the cloud of gas and dust from which our solar system formed, and this injection must have occurred no more than a few million years before the sun began to coalesce. The most likely source for these isotopes is a supernova, the explosive death of a massive star, which produces both aluminum-26 and iron-60 in abundance, and which would have had exactly the right kind of energy to both inject these materials into a nearby molecular cloud and to compress that cloud, triggering its collapse. The picture that emerges is one in which a massive star, perhaps 30 or 40 times the mass of our sun, lived out its brief and brilliant life somewhere in the vicinity of a cold, dark molecular cloud. When that star exhausted its fuel and exploded as a supernova, the blast wave raced outward at thousands of kilometers per second, carrying with it the freshly forged heavy elements from the star's core and outer layers. When this wave encountered the edge of the nearby cloud, it did two things simultaneously. It deposited some of these radioactive isotopes into the cloud material, and it compressed the cloud, squeezing it and increasing its density until gravity could take over and begin the process of collapse. In this way, The death of one star may have been directly responsible for the birth of another, our Sun, and by extension for the formation of Earth and all the life upon it. This process of externally triggered star formation is not unique to our solar system, of course, but appears to be a widespread phenomenon throughout the galaxy, and astronomers have developed several models to describe how it works in different contexts. One of the most important of these is known as the collect and collapse model, which describes how the expanding bubbles of ionized gas around young, hot stars can sweep up the surrounding neutral material and eventually trigger new episodes of star formation. When a massive O-type or B-type star forms within a molecular cloud, it emits such intense ultraviolet radiation that it ionizes the hydrogen gas around it, creating what is called an HII region, the Roman numerals HII referring to ionized hydrogen as opposed to neutral hydrogen, which is designated HI. This ionized gas is much hotter than the surrounding neutral material, typically around 10,000 degrees compared to just 10 or 20 degrees for the cold molecular gas, and this temperature difference creates a pressure difference that causes the HI region to expand outward into the cloud. As the HI region expands, it acts rather like a snowplow, sweeping up the neutral gas ahead of it and compressing it into a dense shell at the boundary between the ionized and neutral material. Over time, this shell can become quite massive, containing perhaps hundreds or even thousands of solar masses of compressed gas. Eventually, if the shell becomes dense enough, it becomes gravitationally unstable and begins to fragment, with individual clumps collapsing under their own weight to form a new generation of stars. These new stars then begin their own lives, and if any of them are massive enough, they in turn create their own HI regions, which expand and compress the gas around them, triggering yet another generation of star formation. In this way, star formation can propagate through a molecular cloud like a slow wave, with each generation of stars giving rise to the next. A beautiful example of this sequential star formation can be observed in the Scorpio-Centaurus OB association, which is the nearest region of recent massive star formation to our solar system, lying at a distance of only about 400 to 500 light-years. An OB association is a loose grouping of young, hot O-type and B-type stars that were born from the same molecular cloud and are still moving through space together, though they are not gravitationally bound and will eventually disperse. The Scorpio-Centaurus association contains several hundred such stars, and careful study of their positions, motions, and ages has revealed that they did not all form at once but rather in a sequence spanning approximately 15 million years. The oldest subgroup, known as Upper Centaurus Lupus, contains stars that are roughly 15 to 16 million years old. The next subgroup, Lower Centaurus Crux, is somewhat younger, with ages around 12 to 13 million years. And the youngest subgroup, Upper Scorpius, contains stars that are only about 10 to 11 million years old. The interpretation of this age sequence is that star formation began in one part of the cloud and then propagated across it over millions of years, with each generation of massive stars triggering the formation of the next through the mechanisms we have been discussing, the expansion of HI regions, the compression of surrounding gas, and perhaps the occasional supernova adding its own contribution to the process. Even now, there are small molecular clouds and dense cores in the region that may be on the verge of forming yet another generation of stars, continuing a process that has been underway for millions of years. The Scorpio-Centaurus association thus provides us with a kind of living laboratory for studying triggered star formation, a place where we can see the entire sequence laid out before us and trace the connections between one generation of stars and the next. On a much grander scale, we find that the collisions and interactions between entire galaxies can trigger enormous bursts of star formation, creating stellar nurseries on a scale that dwarfs anything we see in our own relatively peaceful Milky Way. When two galaxies pass close to one another or merge together, the gravitational forces involved can compress the gas within them on a galactic scale, driving the formation of thousands or even millions of new stars in a relatively short period of time. These events are known as starbursts, and they represent some of the most vigorous star-forming activity in the universe. Perhaps the most famous example of a starburst triggered by a galaxy collision is the Antennae galaxies, a pair of interacting spiral galaxies located approximately 45 million light-years away in the constellation Corvus. These two galaxies, catalogued as NGC 4038 and NGC 4039, began their encounter perhaps 200 to 300 million years ago and are now in the process of merging together, their spiral arms stretched and distorted into long tidal tails that extend outward from the central region like the antennae of an insect, which is how the system received its name. Within the overlap region where the two galaxies are colliding, observations have revealed the presence of more than 1,000 young, massive star clusters, often called superstar clusters because of their exceptional size and brightness. These clusters are far more luminous and contain far more stars than the typical open clusters found in our own galaxy, with some of them containing the equivalent of 1 million solar masses of stars packed into a region only a few tens of light years across. They are, in essence, globular clusters in the making, though most of them will likely disperse over time rather than remaining bound together. The rate of star formation in the antennae is estimated to be roughly 10 to 20 times higher than the normal rate in an undisturbed spiral galaxy, making it one of the most productive stellar nurseries in the nearby universe and a dramatic illustration of how external events can trigger massive episodes of star birth. Another mechanism by which nearby stars can trigger the formation of new stars is through the radiation-driven implosion of small, dense globules of gas. We have mentioned these globules before, the dark, compact clouds that are sometimes seen silhouetted against the bright backgrounds of HI regions. When such a globule is located near a hot O-type star, the intense ultraviolet radiation from that star can ionize and evaporate the outer layers of the globule, creating a bright rim on the side facing the star and causing the globule to lose mass over time. However, this process also has another effect. The pressure from the ionized gas and the radiation itself can compress the globule from the outside, driving a shockwave into its interior and potentially triggering gravitational collapse. If the globule was already marginally stable, this external compression can push it over the edge, causing it to form one or more low-mass stars in a process that might not have occurred, or might have occurred much later, without the influence of the nearby massive star. The recognition that spiral arms are particularly active sites of star formation, and that the stars within them may trigger the formation of subsequent generations of stars, has a distinguished history. In 1953, the American astronomer William Wilson Morgan, working at Yerkes Observatory, presented evidence that young, luminous O-type and B-type stars in the Milky Way are concentrated along distinct spiral arms, a finding that helped establish the spiral structure of our own galaxy and also suggested that these arms represent regions of enhanced star formation. Morgan's work built upon earlier ideas that spiral arms might be associated with density waves moving through the galactic disk, regions of slightly higher density that compress the gas as it passes through them and thereby trigger the formation of new stars. This picture has become a standard part of our understanding of galactic structure and explains why the brightest, younger stars are found predominantly in the spiral arms while older stars are more uniformly distributed throughout the disk. Finally, we should mention what is perhaps the most spectacular stellar nursery in the local group of galaxies, a region known as 30 Doradus, or the Tarantula Nebula, located in the Large Magellanic Cloud, a small satellite galaxy of the Milky Way at a distance of approximately 160,000 light-years. This extraordinary region is forming stars at a rate roughly 100 times greater than the average for similar volumes of space in our galaxy, making it a true starburst region in miniature and the most active site of star formation in our galactic neighborhood. At its heart lies a dense cluster called a 136, containing some of the most massive stars known, with individual stars estimated at 100 to 200 more solar masses, blazing with luminosities millions of times that of our Sun. The nebula itself is so bright that if it were located at the same distance as the Orion Nebula, it would cast visible shadows on Earth and would be easily visible in the daytime sky. The 30 Doradus region provides astronomers with an unparalleled opportunity to study the processes of massive star formation and triggered star birth under conditions far more extreme than anything found in the Milky Way today, and it may represent a nearby analog to the intense star-forming regions that were common in the early universe when galaxies were young and gas-rich. Here, then, in this distant corner of the local group, we find a stellar nursery operating at its most vigorous, a place where new stars are being born at a furious rate and where the cycle of stellar birth, death, and rebirth plays out on timescales almost imaginable to us. And yet, Even here, the fundamental processes are the same as those we have been discussing: the compression of gas, the onset of gravitational collapse, the fragmentation into individual protostars, and the slow emergence of new suns from the darkness of the interstellar medium. It is all, in the end, a matter of gravity and time and the gentle accumulation of matter, played out across scales both vast and intimate, from the collision of galaxies to the quiet contraction of a single core of gas that will one day become a star not unlike our own. When we look up at the night sky, the stars appear to us as solitary points of light, each one seemingly alone in the vast darkness, but this impression of stellar solitude is, as it turns out, rather misleading, for the universe has a strong preference for companionship, and most stars do not form alone but rather emerge from their natal clouds alongside one or more siblings, bound together by gravity into systems that will orbit one another for billions of years, dancing slowly through space, in gravitational embraces that began in the very first moments of their existence. The statistics of stellar multiplicity are really quite remarkable when one takes the time to consider them carefully, and decades of patient observation have revealed that somewhere between 50 and 70% of stars similar to our own Sun form as members of binary or multiple star systems, meaning that the solitary nature of our Sun, drifting through the galaxy without a stellar companion, actually places it in the minority among its peers, a single star in a cosmos that seems to favor pairs and triplets and even larger stellar families, all born together in the same nurturing clouds of gas and dust. Four more massive stars, those brilliant blue giants that burn so fiercely and live such comparatively brief lives. The tendency toward multiplicity is even more pronounced, with observations suggesting that 80% or more of these massive stars have at least one companion, and many have several, as though the same processes that allow a cloud to gather enough material to form a truly massive star also naturally produce the conditions for multiple stellar births in close proximity. Siblings that will spend their entire existence in gravitational conversation with one another. The foundation of our modern understanding of binary star statistics among solar-type stars rests substantially upon a comprehensive survey conducted by Antoine Duquesnoy and Michel Mayer, whose work published in 1991 provided what became a benchmark study for the field, carefully cataloging the properties of binary systems containing stars similar to our Sun and establishing the statistical framework that subsequent researchers would build upon for decades, their patient observations, revealing the distribution of orbital periods and mass ratios and eccentricities that characterize these systems, all gathered through years of careful measurement and analysis. The question of how stars come to have companions, how the process of star formation naturally produces pairs and triplets rather than isolated individuals, has occupied theorists for many years, and two principal mechanisms have emerged from this contemplation, each offering a different pathway to stellar multiplicity, and both likely playing important roles in populating the galaxy with binary and multiple star systems, depending on the particular conditions within any given stellar nursery. The first mechanism is known as disk fragmentation, and it begins with a single protostar surrounded by its accretion disk, that flattened structure of gas and dust that we have spoken of before, spiraling slowly inward to feed the growing star at its center, and under certain conditions, when the disk becomes sufficiently massive and cool, gravitational instabilities can develop within the disk itself, perturbations that grow and amplify until portions of the disk collapse under their own gravity to form additional protostars, siblings born from the same disk that was originally nurturing just one stellar embryo, now suddenly hosting two or three or even more. The second mechanism, known as turbulent fragmentation, operates on larger scales and earlier in the process, occurring when the original dense core within the molecular cloud, the concentration of gas that will eventually form stars, fragments into multiple pieces during its initial collapse, the turbulent motions within the cloud creating density variations that evolve into separate centers of collapse, each one destined to become a protostar in its own right, born at nearly the same moment, from the same parent core but forming as distinct objects from the very beginning of the collapse process. Both mechanisms leave their signatures on the resulting binary and multiple star systems, with disk fragmentation tending to produce companions at closer separations and turbulent fragmentation often yielding wider pairs, though the reality is certainly more complex than this simple division suggests, with dynamical interactions and orbital evolution continuing to shape these systems long after their initial formation. Companions migrating inward or outward, orbits circularizing or becoming more eccentric, the dance continuing and evolving over millions of years. The Atacama Large Millimeter Array, that remarkable collection of radio telescopes high in the Chilean desert, has provided some of the most detailed observations of multiple star formation in progress, peering through the obscuring dust to reveal the structures hidden within stellar nurseries. And in 2016, observations of a system known as L1448 IRS-3b revealed a truly spectacular example of stellar multiplicity caught in the act of formation, a triple protostar system embedded within a single large disk, the three young stars arranged in a configuration that spoke clearly to the processes of their birth. The L1448 IRS-3b system showed beautiful spiral arms extending through the surrounding disk, structures created by the gravitational interactions between the three protostars, their mutual influence sculpting the gas and dust into sweeping curves that trace the dynamics of the system like brushstrokes left behind by an artist. And these observations provided strong evidence for disk fragmentation as the mechanism that had produced this particular stellar trio, the spiral arms being characteristic signatures of gravitational instability in a massive disk, the same instability that had apparently caused the disk to fragment and form multiple stellar objects. One of the most familiar examples of a multiple star system lies remarkably close to us, cosmically speaking, for the Alpha Centauri system, our nearest stellar neighbor beyond the Sun, is itself a hierarchical triple, containing three stars bound together in a gravitational arrangement that has persisted for billions of years, a nearby example of the multiplicity that characterizes so much of the stellar population throughout the galaxy. Alpha Centauri A and Alpha Centauri B form a relatively close pair, two stars orbiting their common center of mass with a period of roughly 80 years, their separation varying as they trace their elliptical paths around one another, sometimes drawing as close as the distance between the Sun and Saturn, sometimes receding to a distance more comparable to the span between the Sun and Pluto, a slow gravitational waltz performed by two stars that are both roughly similar to our own Sun, one slightly larger and brighter, the other somewhat smaller and cooler. The third member of the system, Proxima Centauri, is a small red dwarf star, much cooler and dimmer than its companions, and it orbits the central pair at an enormous distance, so far removed that it takes hundreds of thousands of years to complete a single orbit, a distant sibling keeping watch from the outskirts of the family, and it is this star, Proxima, that actually holds the title of the closest individual star to our Sun, a mere 4.2 light-years away, though it is so dim that it cannot be seen without a telescope. Not all stars born together remain together, for the gravitational dynamics of multiple star systems can be complex and sometimes unstable, and under certain circumstances, close encounters between stars in a young system can result in one member being ejected entirely, flung outward at high velocity to begin a solitary journey through the galaxy, a runaway star cast out from its birthplace by the gravitational slingshot of its former companions. The phenomenon of stellar ejection was investigated with particular elegance by the Dutch astronomer Adrian Blau, who in 1961 traced the motions of several fast-moving stars backward through time, like rewinding a film to discover where the actors had been standing at the beginning of the scene, and his work revealed that the stars Ae Aurigae and Mu Columbi, now located in completely different parts of the sky, had both originated from the same region in the Orion Nebula approximately 2.5 million years ago, ejected in opposite directions by the same dynamical event. The culprit, or rather the remaining member of the interaction, was identified as the Iota Oriona system, a multiple star system still residing in the Orion region, and the reconstruction of this ancient event provided compelling evidence for n-body dynamical ejection, the process by which gravitational interactions in a small group of stars can transfer enough energy to one member to unbind it completely from a system, sending it racing away while the remaining stars settle into a more stable configuration, the violent reorganization of a stellar family that leaves some members orphaned and wandering. These runaway stars can travel enormous distances over millions of years, crossing from one spiral arm of the galaxy to another, and their high velocities betray their dramatic origins, for ordinary stars born in relative isolation do not achieve such speeds. And so when astronomers encounter a fast-moving star far from any obvious birthplace, they know to look backward along its trajectory, seeking the nursery from which it was expelled, the family gathering it departed so abruptly long ago. The disks of gas and dust that surround young stellar systems take on particularly interesting configurations when multiple stars are present, for the gravitational influence of two or more stellar objects carves and sculpts the surrounding material in complex ways. And one especially intriguing arrangement is the circumbinary disk, a disk of material that surrounds both stars of a binary pair rather than orbiting just one, a shared envelope of gas and dust encircling the stellar couple like a ring around two dancers. The GG Tauri system has provided astronomers with a beautiful example of such a circumbinary disk, observed in detail and revealing the intricate structures that arise when two young stars share a common disk, the gravitational interactions between the stars and the disk creating gaps and rings and asymmetries that encode information about the masses and orbits of the stellar components, a cosmic laboratory for studying the interplay between stars and their surrounding material during the formative epochs of planetary system development. Circumbinary disks are particularly fascinating because they represent the environments in which circumbinary planets might form, worlds that would orbit both stars of a binary pair, experiencing two sunrises and two sunsets, living under skies illuminated by stellar companions of different colors and brightnesses. And such planets have indeed been discovered around older binary star systems, suggesting that the circumbinary disks observed around young systems like GG Tauri may eventually give rise to planetary systems quite unlike our own. The detection of binary and multiple star systems requires a variety of techniques, for stellar companions reveal themselves in different ways depending on the geometry of their orbits and their separations from one another and their relative brightnesses. And some binaries are easily visible as two distinct points of light through a telescope, but many others are too close together to be resolved visually, their light blending into what appears to be a single star. Spectroscopic binary detection, one of the most powerful techniques for revealing close companions, was pioneered by Edward Pickering at Harvard Observatory, who in 1889 noticed something peculiar in the spectrum of the star Mizar, for the dark absorption lines in the star spectrum. Those fingerprints that reveal the chemical composition of stellar atmospheres appeared to split and merge periodically, doubling into pairs and then recombining into single lines in a regular rhythm that betrayed the presence of an unseen companion. The explanation for this splitting of spectral lines lies in the Doppler effect, the same phenomenon that causes the pitch of a passing train's whistle to rise and fall, for when a star moves toward us its light is shifted slightly toward the blue end of the spectrum, and when it moves away the light shifts toward the red. And in a binary system where both stars are orbiting their common center of mass, there are times when one star is approaching while the other is receding, causing their spectral lines to separate, and times when both are moving across our line of sight rather than toward or away, causing the lines to overlap once more. This technique of spectroscopic binary detection opened up an entirely new population of stellar systems to investigation, for many binaries orbit so closely together that no telescope could ever resolve them as separate points of light, their annual motions across the sky indistinguishable from those of single stars, yet their spectra betray the truth of their duplicity, the rhythmic shifting of their spectral lines revealing the orbital dance that visual observation alone could never perceive. And so we find that stellar nurseries are not merely birthplaces of individual stars but are instead the origins of stellar families, systems of two or three or more stars born together from the same collapsing clouds, bound by gravity into associations that may last for billions of years or may be disrupted by dynamical interactions that send some members wandering alone through the galaxy. The processes of star formation naturally producing the rich variety of stellar configurations that populate the cosmos, from close binaries that orbit in mere days to wide pairs that take millennia to complete a single circuit, all of them born together in the quiet depths of molecular clouds, siblings emerging from shared natal material into the vast and patient universe that awaits them. The space around us, the region through which our sun and its family of planets drift in quiet procession, is not quite like the rest of the galaxy. It is emptier, warmer, and more diffuse than the typical stretches of interstellar medium that fill the vast distances between stars. We exist within a kind of cosmic clearing, a great cavity blown into the fabric of gas and dust that otherwise permeates the Milky Way, and this clearing has a name that suits its nature rather well. It is called the local bubble, and understanding its origins and its boundaries helps us appreciate the gentle violence that shaped the neighborhood our solar system now calls home. The local bubble extends for roughly 1,000 light-years in most directions from the Sun, though its shape is irregular and its edges are not sharply defined. Within this enormous volume, the density of interstellar gas is perhaps 10 times lower than in the surrounding regions of the galaxy. Where the typical interstellar medium might contain one atom of hydrogen in every cubic centimeter of space, the local bubble holds far fewer, creating a kind of rarefied emptiness that allows certain wavelengths of light to travel more freely and permits us to observe distant objects with less interference than astronomers working from a denser location might experience. The discovery of this feature came gradually, through patient observation and careful analysis of starlight passing through the space between us and more distant suns. During the 1970s and continuing into the 1980s, researchers noticed something curious in the absorption lines of sodium when they studied the spectra of nearby stars. Absorption lines appear when light from a star passes through intervening gas, and atoms in that gas absorb specific wavelengths corresponding to their particular electron transitions. Sodium atoms leave distinctive signatures in starlight, and by measuring these signatures for many stars at various distances and directions, astronomers could map the distribution of gas surrounding the Sun. What they found was unexpected. The sodium absorption was weaker than anticipated for stars within a few hundred light-years, suggesting that the intervening space contained less gas than models had predicted. As observations accumulated and techniques improved, the picture became clearer. We inhabit a bubble, a region where something has swept away much of the material that once filled interstellar space, leaving behind this peculiar void through which our solar system travels. The question of what created the local bubble occupied researchers for decades, and the answer, when it came, involved the deaths of massive stars in considerable numbers. Supernovae, those catastrophic explosions marking the end of stellar lives for the most massive suns, release tremendous amounts of energy into their surroundings. A single supernova can outshine an entire galaxy for a brief time, and the shockwaves from such an explosion can push interstellar gas outward for hundreds of light-years, compressing it into dense shells while leaving behind hot, rarefied cavities. Research published in 2016 by Dieter Breitschwert and colleagues at the Technical University of Berlin presented a detailed model for the local bubble's formation. Their work suggested that not one but somewhere between 14 and 20 supernovae occurred in this region over a period spanning 10 to 20 million years. Each explosion added its energy to the growing cavity, pushing the walls outward and maintaining the high temperature of the interior gas. The cumulative effect of these sequential detonations carved out the 1,000-light-year void we observe today, creating a monument to stellar death that we inhabit without ever having witnessed the events that formed it. The source of these supernovae appears to have been a moving group of stars known as the Scorpio-Centaurus Association, which is the nearest region of recent star formation to our solar system. This association contains many young, massive stars, and it has been moving through this part of the galaxy for millions of years. As it traveled, its most massive members exhausted their nuclear fuel and exploded, one after another, each adding to the expanding cavity. The timing and positioning of these events, reconstructed through careful modeling, aligns well with the observed properties of the local bubble and its surrounding structures. Our Sun was not always a resident of this cleared region. The solar system has its own motion through the galaxy, orbiting the galactic center and drifting relative to nearby stars and gas clouds over millions of years. Current estimates suggest that the Sun entered the local bubble approximately 5 to 10 million years ago, crossing from denser interstellar medium into the evacuated cavity where we now reside. Before that crossing, our solar system would have experienced a different environment, with more interstellar material pressing against the outer reaches of the Sun's influence, the region we call the heliosphere. The transition into the local bubble may have had subtle effects on conditions in the outer solar system, and perhaps even on the flux of cosmic rays reaching the inner planets, though teasing apart such influences from other factors affecting Earth's climate and geology over millions of years remains challenging. What is clear is that our current position within this bubble represents a relatively recent chapter in the solar system's long journey around the galaxy, a chapter that began when our ancestors' ancestors' ancestors were only just beginning to emerge in the African forests. Within the local bubble, conditions are not perfectly uniform. The Sun currently travels through a small, denser region called the local interstellar cloud, sometimes affectionately abbreviated as the LIC. This cloud is tiny by cosmic standards, perhaps 30 light-years across, and it contains gas with a density of approximately 0.3 atoms per cubic centimeter. This is still far less dense than typical interstellar medium, but noticeably denser than the most evacuated portions of the local bubble. The local interstellar cloud has its own motion, flowing through the bubble, and the Sun is thought to have entered this small cloudlet perhaps 44,000 years ago, with an estimated exit occurring in another 10 to 20,000 years. Measurements of the cloud come from various sources, including observations of nearby stars and direct measurements from spacecraft traveling through the outer solar system. The Voyager probes, now crossing into interstellar space, have provided data about the boundary between the solar wind and the interstellar medium, confirming the presence of this thin but measurable material pressing gently against our heliosphere. The local bubble does not exist in isolation. It connects to other similar structures, forming a network of cavities and tunnels carved by ancient supernovae throughout this region of the galaxy. Adjacent to our bubble lies the Lupi superbubble, associated with the Scorpius-Centaurus Association, and other structures with names like the Loop 2 and Loop 3 superbubbles. These features interconnect in places, allowing hot gas to flow between them, and together they form a kind of Swiss cheese structure in the local interstellar medium, with dense walls of swept-up gas surrounding relatively empty interiors. Recent research has revealed that the local bubble continues to influence its surroundings in measurable ways. A study published in 2022 by Catherine Zucker of the Space Telescope Science Institute and her collaborators used three-dimensional maps of nearby molecular clouds to demonstrate that the expansion of the local bubble has triggered star formation in several regions surrounding it. As the supernova-driven shockwaves pushed outward over millions of years, they compressed the interstellar medium at the bubble's edges, creating the dense conditions necessary for gravitational collapse and the birth of new stars. The Taurus molecular cloud, located at the edge of the local bubble, shows evidence of this compression-triggered star formation, as does the Ophiuchus star-forming region and several other nearby stellar nurseries. Zucker's team traced the positions and motions of these clouds in 3 dimensions, finding that they sit on the surface of the expanding bubble like beads on an inflating balloon. The star formation occurring in these regions today is a direct consequence of supernovae that exploded millions of years ago, connecting the deaths of ancient stars to the births of new ones in a cycle that continues around us even now. This finding places us quite literally at the center of an expanding shell of star formation, watching new stellar nurseries emerge on all sides at distances of a few hundred light-years. The young stars forming in Taurus and Ophiuchus are our distant neighbors, coming into being because the same forces that cleared the space around our Sun also compressed the gas at the bubble's edges to the point where gravity could take hold. It is a gentle reminder that stellar birth and stellar death are not separate processes but rather parts of a single, interconnected cycle that shapes the galaxy over millions of years. Evidence of the supernovae that carved the local bubble has been found not only in astronomical observations but also in the geological record of our own planet. Deep-sea sediments and manganese crusts recovered from the ocean floor contain traces of iron-60, a radioactive isotope that does not form naturally on Earth but is produced in significant quantities during supernova explosions. When a nearby star explodes, some of this freshly forged iron-60 spreads outward with the debris, eventually settling onto planets and moons in the surrounding region. Measurements of iron-60 in deep-sea crusts, particularly in samples dated to approximately 2 to 3 million years ago, show elevated levels that indicate a nearby supernova during that period. This timing corresponds roughly to the later stages of the local bubble's formation and suggests that at least one of the supernovae responsible for our cosmic cavity occurred close enough and recently enough to leave its signature in Earth's geology. The amount of iron-60 detected implies a supernova distance of perhaps 100 to 300 light-years, close enough to deposit measurable material but far enough to pose no serious threat to life on Earth. Additional iron-60 deposits have been found in samples dated to around 7 to 8 million years ago, suggesting another period of nearby supernova activity. These findings provide a kind of geological corroboration for the astronomical models of local bubble formation, connecting events in deep space to physical evidence we can hold in our hands, or at least examine in our laboratories. The atoms of iron-60 in those sediments were forged in the cores of massive stars that no longer exist, carried across light years of space by the same explosions that cleared our cosmic neighborhood, and finally came to rest at the bottom of Earth's oceans, where they waited millions of years for curious beings to discover them and wonder at their origins. The local bubble, then, is far more than an empty region of space. It is a record of stellar history, a monument to stars that lived fast and died young, leaving behind this cleared space through which our sun now drifts. Its walls are sculpted by ancient shockwaves, its edges give birth to new stars, and its existence has shaped the cosmic environment our planet has experienced for millions of years. We are not passive observers of this structure, but inhabitants of it, our solar system having wandered into this cavity at some point in the geological past and continuing its slow journey through the warm, thin gas that fills the bubble's interior. The sun will not remain within the local bubble forever. Eventually, in millions of years, our solar system's orbit around the galactic center will carry us back into denser regions of interstellar medium, or perhaps into other bubbles carved by other supernovae in other epochs. The galaxy is constantly reshaping itself through these cycles of stellar death and rebirth, with bubbles expanding and fading, clouds compressing and collapsing, and new stars igniting to begin the process anew. For now, we rest within this particular clearing, this particular moment in a very long story, surrounded by the evidence of explosions we never saw and the beginnings of stars we may never visit, all of it continuing in the same unhurried manner it has followed for millions of years, and will follow for millions more. As we come now to consider what lies ahead, we find ourselves in rather a fortunate position, one in which the tools for understanding stellar nurseries are becoming ever more refined, ever more sensitive, and ever more capable of revealing the quiet processes that unfold across such vast distances and such immense spans of time. The coming years and decades promise a continued deepening of our knowledge, not through any single dramatic breakthrough, but through the patient accumulation of observations gathered by instruments scattered across our planet and positioned in the cold darkness of space, each one contributing its own particular view to the gradually assembling picture of how stars come to be. Among the most anticipated of these instruments is the Nancy Grace Roman Space Telescope, which is planned for launch around the year 2027, and which will carry with it a remarkable capability for surveying the sky in ways that have not previously been possible. Named in honor of Nancy Grace Roman, who was instrumental in the development of the Hubble Space Telescope and who dedicated her career to expanding humanity's view of the cosmos, this new telescope will orbit far above our atmosphere and will turn its attention to many questions, including the nature of dark energy and the detection of distant planets. But it will also provide unprecedented views of star-forming regions within our own galaxy. The telescope's primary instrument, known as the Wide Field Instrument, contains a detector array of some 300 megapixels, which is a rather large number but which simply means that it can capture extremely detailed images across a field of view that is roughly 100 times larger than that of the Hubble Space Telescope, though with comparable sharpness and clarity. This combination of wide coverage and fine detail is particularly valuable when studying stellar nurseries, which are often spread across many degrees of sky and contain structures at many different scales, from the vast molecular clouds themselves down to the individual protoplanetary disks surrounding newly forming stars. With the Roman Space Telescope, astronomers will be able to survey entire star-forming complexes in a single observation, or in a series of observations that can be stitched together, building up comprehensive maps that show not only where stars are forming but also how the various stages of star formation are distributed across the cloud, how the feedback from young stars is shaping the surrounding material, and how the process varies from one region to another. This kind of wide-field survey work is essential for understanding star formation as a statistical process, one that involves many thousands of stars forming in roughly similar conditions, and the Roman Space Telescope will contribute greatly to this understanding in the years following its deployment. Meanwhile, The James Webb Space Telescope, which began its scientific operations in the year 2022, continues to provide observations of extraordinary quality, revealing aspects of stellar nurseries that were previously hidden from view. The Webb telescope is particularly sensitive to infrared light, including the mid-infrared wavelengths that are emitted by warm dust and by certain molecules that exist within the disks of material surrounding young stars, and this sensitivity has already yielded remarkable results in its early years of operation. One example that illustrates the telescope's capabilities comes from observations made in 2023 of a young protoplanetary disk known as D203-506, which is located within the Orion Nebula, that familiar region of star formation visible as a faint smudge in the sword of the constellation Orion. The observations of D203-506 revealed the presence of water vapor within the inner regions of the disk, providing direct evidence that the raw materials for water, and by extension the raw materials that might one day contribute to habitable conditions on planets, are present from the very earliest stages of planetary system formation. Water is, of course, a molecule of particular interest when considering the potential for life elsewhere in the universe, and detecting it within a protoplanetary disk, in the region where rocky planets might eventually form, suggests that the delivery of water to such planets could be a natural part of the formation process rather than a rare or unusual occurrence. The Webb telescope continues to observe many other protoplanetary disks, and each observation adds to our understanding of the chemistry occurring within these systems, the distribution of various molecules, and the conditions under which planets begin to take shape. Looking somewhat further into the future, there is a concept under study that goes by the name of the Habitable Worlds Observatory, which represents an ambitious proposal for a space telescope that would be specifically designed to search for signs of life on planets orbiting other stars. While the primary goal of such a mission would be the direct imaging of Earth-like planets around nearby stars and the analysis of their atmospheres for potential biosignatures, the capabilities required for such observations would also be extraordinarily valuable for studying the chemistry of protoplanetary disks. Understanding the composition of these disks, the abundance of various organic molecules, the distribution of water and other volatiles, and the processes by which these materials are incorporated into forming planets, is essential for interpreting any eventual detections of biosignatures on mature planets. The Habitable Worlds Observatory concept thus connects the study of stellar nurseries to the broader question of life's place in the universe, though such a mission, if approved and funded, would not launch for many years yet, perhaps not until the 2040s or beyond. Returning our attention to the surface of the Earth, we find that significant developments are also underway in ground-based astronomy, and perhaps none more substantial than the construction of the Square Kilometre Array, a radio telescope of unprecedented scale that will, when completed, provide capabilities far exceeding those of any existing radio observatory. The Square Kilometre Array, often referred to simply as the SKA, is not a single telescope but rather a vast network of individual antennas spread across two sites, one in the remote outback of Western Australia and the other in the Karoo region of South Africa. When operational, which is expected in the late 2020s, with full capabilities developing over the years that follow, this array will have a total collecting area approaching 1 square kilometre, though the antennas themselves will be distributed across distances of many kilometres, creating an instrument of extraordinary sensitivity and resolution. For the study of stellar nurseries, the Square Kilometre Array will provide the ability to detect and map magnetic fields within the dense cores where stars are beginning to form. Magnetic fields play an important role in the collapse process, providing a form of support against gravity and influencing the way in which material flows onto the forming protostar, and yet they are notoriously difficult to measure directly. Radio observations, particularly observations of certain polarized emissions and of a phenomenon known as Z-band splitting, in which spectral lines are subtly shifted by the presence of magnetic fields, can reveal the strength and orientation of these fields, and the Square Kilometre Array will be able to perform such measurements with far greater sensitivity than has previously been possible. The Australian and South African locations were chosen in part for their radio quietness, being far from the interference generated by cities and electronic devices, and in part for their complementary views of the sky, allowing observations of star-forming regions throughout the Milky Way. Another ground-based facility that will contribute to our understanding of stellar nurseries is the Vera C. Rubin Observatory, which is nearing completion in the mountains of northern Chile. This telescope will conduct what is known as the Legacy Survey of Space and Time, a 10-year observing program during which the entire visible sky will be imaged repeatedly, building up a comprehensive record of how objects change in brightness over time. Young stellar objects, meaning protostars and pre-main sequence stars still in the process of settling into their stable configurations, are often variable, flickering and fluctuating in brightness as material falls onto their surfaces from surrounding disks, as hot spots rotate in and out of view, and as changes occur in the obscuring dust that lies along our line of sight. By observing the same regions of sky night after night, over years, the Rubin Observatory will identify and characterize many thousands of these variable young stars, providing statistical information about the processes occurring during these early stages of stellar life and revealing rare or unusual phenomena that might otherwise go unnoticed. We should also acknowledge the contributions of a mission that has already been operating for some years, but whose impact on the study of stellar nurseries continues to grow. The Gaia spacecraft, operated by the European Space Agency, has been measuring the positions and motions of stars throughout our galaxy with extraordinary precision, and among its many contributions has been the determination of accurate distances to young stellar clusters, those groups of stars that have formed together from the same molecular cloud and that are still located relatively near their birthplaces. Knowing the precise distance to such a cluster is essential for converting observed brightnesses into true luminosities, for determining the physical sizes of structures, and most importantly, for estimating the ages of the stars involved. Before Gaia, distance estimates for many clusters were uncertain by 10 or 20%, which translated into significant uncertainties in derived ages, but Gaia's measurements have reduced these uncertainties dramatically, allowing astronomers to construct much more reliable timelines for the star formation process. This has revolutionized our understanding of how long the various stages of stellar evolution take, how quickly disks dissipate, and how the properties of young stars evolve over their first tens of millions of years. Looking further ahead, to concepts that are still in the early stages of development, we might consider the Atacama Large Aperture Submillimeter Telescope, often abbreviated as ATLAST, which represents a proposal for a new submillimeter telescope that would be located in the Atacama Desert of Chile, at high altitude where the atmosphere is particularly dry and transparent to the submillimeter wavelengths that are absorbed by water vapor at low elevations. The proposed telescope would have a primary mirror of perhaps 50 meters in diameter, far larger than any existing submillimeter facility, and would be capable of mapping molecular clouds not only within our own galaxy but across entire nearby galaxies as well. Such observations would allow astronomers to study star formation in environments quite different from our own galactic neighborhood, in galaxies with different chemical compositions, different densities of gas and dust, and different histories of stellar activity, and would thus help to determine which aspects of star formation are universal and which depend on local conditions. ATLAST remains a concept rather than an approved project, and many years of development would be required before such a telescope could begin observations, but it represents the kind of ambitious thinking that drives progress in astronomy. All of these instruments, whether already operating, under construction, or still in the conceptual stage, share a common purpose, which is the gradual and careful accumulation of knowledge about how stars form. No single observation will answer all questions, no single telescope will reveal all secrets, but together, over time, the data gathered by these many instruments will continue to fill in the picture, adding detail where there was once only vague impression, confirming or refuting theoretical predictions, and occasionally revealing unexpected phenomena that send theorists back to their models with new puzzles to solve. The study of stellar nurseries is a patient enterprise, as befits its subject, and the future missions we have considered here represent the next steps in a journey that will continue for as long as humans remain curious about the workings of the cosmos. And so, as you lie here, perhaps with eyes growing heavy and thoughts beginning to drift, you might take some comfort in knowing that even as you rest, instruments around the world and beyond it are quietly collecting photons, radio waves, and other messengers from distant clouds where new stars are beginning their long lives. The work goes on, steady and unhurried, much like the processes it seeks to understand, and in time, the fruits of this work will become part of our common knowledge, another layer added to humanity's understanding of the universe in which we find ourselves.